Okay, I think it is time, and Assalamu alaikum wa rahmatullah. I welcome you all. Welcome to our guest speakers and distinguished faculty and our vice rector. We'll be starting in a few seconds. I will give the floor to our vice rector for the opening remarks, and I will explain how to ask questions, how to if you have any you can if you have any questions in the chat, or we will talk about that after the opening remarks by Dr. Ali Sheikhi. Dr. Sheikhi, the floor is yours.
Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon, everyone. I am really and extremely happy and glad to welcome you all to this technical forum. And I'm also happy that maybe this is, I think, my first forum to inaugurate. And fortunately, also it came through my home department, electrical engineering. I am a little bit biased, of course. Plus also, I'd like to thank the Interdisciplinary Research Center for Communication System and Sensing, headed by Dr. Ali Mugabil, for also co-organizing this important forum about 6G networks, opportunity and challenges. I'd like really to thank all the participants, my colleagues, my previous colleagues and friends from KAUST, from other places, also from the electrical engineering, for really seeing these excellent put together important titles to tackle the 6G network. We know that the 6G network will be the successor to the 5G cellular technology. And of course, I think we are talking here about higher frequency than the previous 5G, and it may provide also more substantial higher capacity and much lower latency. And of course, all of these definitely will come with some challenges that I'm sure that it will be addressed through this forum. So I'm happy that we are really ahead of the curve. We are thinking forward. I'm happy that the participation of both the academic and the academic department and the research sector. And as the VP for Research and Innovation, this is our new KFUPM, is we are really trying to remove the boundary between the departments and the centers. So as you know, maybe just in a nutshell, I'd like to mention that we went through a transformation. The university KFUPM went through a transformation. It started with the academic and then with the research sector. And you can see some of the outcomes of these transformation kicks and those centers and these forums as a result of this transformation, and breaking the walls and the silos between the research sector and the academic department is one of the most important pillars in the transformation. And I'm really happy and glad to see these happening right now. So without taking much of your time, I was really I wanted really to talk more about the research transformation, because I am the VP of Research and Innovation, but maybe in another opportunity. Other than that, I'd like to welcome you again to this forum. I hope, inshallah, all the best for all of you to have really fruitful discussion. And maybe we can really implement some of these, because we are really looking in the research sector into really those big challenges that will have a direct effect as much as possible to our community and to our kingdom. This is what we need really, and we need really to collaborate more closely with the industry, with the other university like KAUST and others. And this is the essence of the whole transformation that KFUPM is undergoing. So without any further ado, I will give you the floor back to you, Dr. Zaidouri. Thank you very much.
Thank you very much, Dr. Ali Sheikhi, for this nice words and officially opening this technical forum. Welcome again all our audience and our distinguished guests and speakers. Just a few words for how the questions will be asked and hopefully answered. So we have, as you have seen in the syllabus or the schedule that you have received, we have 5 sessions, about 20 to 30 minutes. I would like the speakers to leave about 5 minutes for questions and answers, or between 3 and 5 minutes. We will reserve if there are more questions, there is at the end at 2:20, there is the panel discussion and the closing remarks. So we will move most of the questions to the last session of panel discussion, where all our speakers will be present and they can answer all your questions and queries. So we are going to give the floor for each speaker. So after the presentation, there will be a few minutes for questions and answers. And so if you want to ask, you can either write in the chat or you can raise your hand and I will give you or allow you to speak, and then you can ask with your own voice or live. So without further ado, I will introduce our first speaker. So our first speaker is Dr. Hesham ElSawy. Dr. ElSawy received his PhD in 2014 from Manitoba, University of Manitoba, Canada. He received many awards and the Outstanding Young Researcher Award for Europe, Middle East, and Africa. And he received the Best Paper Award in 2020 from IEEE ComSoc, Best Tutorial Paper Award in 2017, and the Best Survey Paper Award in 2018. His research interests include statistical modeling, wireless networks, stochastic geometry, queuing analysis, and cybersecurity for wireless networks. Today, he's going to talk about privacy and cybersecurity in massive wireless networks. So I invite Dr. Hesham ElSawy to take the floor and share his slides and or presentation. Dr. Hesham.
Thank you, Dr. Zuduri. Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. Inshallah, today I will be talking about one of the challenges of 6G networks. So we'll start today by the challenges, and then the rest of the speakers will talk to you about the opportunities. So today I will start by talking about privacy and cybersecurity in massive wireless networks. And indeed, 6G is one of these networks. So let me see. Can you see my slides, right?
Yes, yes.
So let's also take the presenter. Okay. So this is the agenda for today. I will start by introduction about 6G. I will not talk much about them because they'll be like addressed later in later presentations. I'll talk about the security threats, some examples of these threats like we have witnessed in the recent years. And then I will talk about the massive network epidemics, which is the main focus of this talk, and some potential solutions and conclusions. So indeed, in 20 minutes, I will not be able to address all of these aspects in details. I'll just give highlights about each of them and then maybe direct you to some resources. So 5G network is actually can be considered as the first generation that integrate the physical and digital world. So in 1G, 2G, 3G, 4G, we have an enhanced mobile experience for human type communication. The 5G networks is actually the first generation that makes a seamless integration between human and machine type communications, and there's a smart cities buzzwords start to come up where we need to control the entire environment. And in this scenario, or the 5G scenario, they define 3 use cases. One of them is enhanced broadband, which is actually the natural evolution of cellular technologies, that we have better experience, better internet access, higher speeds, higher capacity, but also they introduced new 2 use cases. One of them is massive connectivity for Internet of Things and ultra reliable low latency communication for mission critical applications. So this is the first generation that has this integration between the physical and digital world. And then the 6G network comes to take this experience even further and make a seamless integration between the digital and physical worlds and also the digital worlds. All of us have been witnessing this metaverse proposals where we will be able to meet virtually, telepresence, this augmented reality, and virtual reality, and this mix between these 3 use cases, where we will have more like control, better experience, and also easier daily life activities. Okay, so what do we need to do that? Actually, and this is some of the use cases. So as you can see, we will have enhanced broadband. This is the usual communication evolution. And then we'll have unconventional data communication. You can see here we'll have implants, we'll have brain-to-brain communications, and this kind of new paradigm of communication, Internet of Body things. We'll have several implants, and also like haptic mouses that we can actually feel what we deal with in the virtual worlds, and so on and so forth. And we have the 3D communication. We'll have satellites, floating base station, flying base stations in different layers in the atmosphere and space. And we'll have this, super, ultra reliable low latency communication for UAVs and for example, connected autonomous vehicles, and so on and so forth. And become when we have every part of the world that is connected. And you can see to achieve this vision, we need many aspects or many improvements in our networks. One of them, which we need actually a huge, or the greatest gap, is in terms of security and privacy, because we can imagine how these things will be penetrating in our life, and and privacy and security will be a major aspect there. So what is the security, or what are the security threats there? So we have most of these, devices, or much of this application are implemented by the users or end users who are untrained and agnostic to these risks or cybersecurity risks. Okay, and then we have multiple vulnerabilities in each device, because these devices are, with the rapid proliferation of these devices and the competition between different vendors, they actually overlook the security aspects. And then we have billions of connected devices. So if you can have these 3 items together, you have very high risk, and this can be exploited by hackers and malicious users to control and have adversary attack on our networks. So now, if we have this integration, and we used to have the cyber threat confined or trapped in the digital world, with these interfaces, we'll have the cyber threats going from the digital world to the physical world to the virtual world. What does this mean? So in the digital world before, what can a hacker do to me? He can at most for example, access my files. He can steal some information. He can for example steal some money, something like that. But when it goes to the physical world, actually there will be some physical consequences, because now this cyber world is connected to actual physical devices. So he can manipulating body implants, for example, for drug diffusers and stuff like that, which can really harm or kill somebody. Major blackouts in cities, deliberate collisions between vehicles, equipment stoppage, in factories, and worker injuries. So now we have the threats going from the cyber world to the physical world. Okay, so these are the physical consequences, and also to the virtual world. So in the virtual world, we can have social engineering. We can actually deceive people and and direct their actions to a certain direction that benefits the adversaries or the attackers. we can have deception and illusions, deep fakes. So for example, I can copy or regenerate your avatar in the virtual world, go talk to people, get some attend meetings and do everything on your behalf in the virtual world. When I talk about virtual or telepresence and so on and so forth, we can do identity theft and so on and so forth. So you can see now that the threats are not just about our data and privacy. It actually, how should I say, it threatens our own safety, okay, in a large scale sense. So this is not just imaginations. Those actually has been, like we have experienced something like that. As you can see, for example, this is a vehicle, and all of these are vulnerabilities. So a user can access any or can access the vehicle through infotainment, for example, services, through the internet access from the telemetrics and and the wireless connectivity. He can access to the car, and this is a situation here where a driver was driving on the highway, and people miles away, or hackers miles away, were able to infiltrate their malicious software through the infotainment system, through the cellular network, and were able to control and crash the car. So you can think that if these hackers can actually control large number of cars, it can be or can lead to disaster effects. So is it worse? Yeah, it can go even worse. As you can see, these two published, newspapers here, or two published news here. We have nearly all US weapon system have critical cybersecurity problem, and this is published 2018. And the cybersecurity in Saudi Arabia had a deadly goal: expert fear another try. And you can see here they want to stop the firm's operation and trigger an explosion. So if the hackers, with this integration with the cyber and physical world, can access this critical, infrastructure, this could be or could lead to the disaster effect. So now let's talk about cybersecurity, and people can ask, you are a wireless communication engineer, what are you coming or what can you offer for cybersecurity? And the answer here is that the privacy and cybersecurity in 5G and beyond system is a collaborative responsibility. Okay, it's not just one-man show. Yeah, that you'll have one, security administrator that will take care of everything. No, it's not like this. It's actually a collaborative approach. And all of us have seen these human firewalls, training. We have seen this phishing emails, like simulators by the ICTC, where they send us some emails, in phishing to train us to how to respond to these security threats. So we need raising awareness of the end user. We need mathematicians to develop new paradigm of cryptography that can be implemented with this system simple device. We need white hat hackers to do penetration testing and make sure that our systems are secure. We need software engineers to develop anti-malware programs. We need network engineers to implement firewalls and security servers and so on and so forth. So now the question comes, as a wireless communication engineer, what value can I bring to this big picture? What is the vulnerability that I can take care of and add to this cybersecurity countermeasures? Okay, so now let's look into the threats, and then from there we can go and see what can I offer. Okay, so malware is a malicious code that is intended to harm a target device, and there are three ways or forms of this malicious malware. One of them is Trojans, and Trojans are, they hide the bad code into a legitimate kind of code that you are somehow, motivated to use. For example, an app store, you have a game, and you download the game, and you get the malware. And the virus is also the same as a Trojan, but it has an ability to replicate itself over different files within the same machine. So to have the infiltration or the spreading of Trojan and viruses, there should be a human involved. Okay, you have to a human should download or click a button, open an email, click a link, so that he can get this virus. The most interesting one, or the most threatening one, is the worm, because it's a kind of a soft malicious code that by itself exploits the vulnerabilities or the connectivity vulnerabilities, and it can replicate itself into other devices. Okay, so you can see here the worm can actually by itself diffuse from one device to another without any interaction between humans. So human awareness or raising the awareness will not help in worm spreading. It can also only help in Trojans and viruses. Okay, so now this comes to the problem definition. So large number of devices are wirelessly connected, and hackers can inject the malware into small set of devices, and then this through the wireless connectivity like Bluetooth, like in large-scale network like LoRa, and device-to-device communication, and so on and so forth. The malware can propagate from one device to another, leading to what is called an epidemic outbreak, where we have many devices infected. And like you can see this animation here, if we have this network and we have this hacker come here, he needs only to infiltrate his malware into a subset of the devices, and this device will actively by themselves automatically look for other devices and start diffusing the malware, and then we'll have a large-scale botnet. All of these devices are under the control of this hacker, where he can generate a big large-scale attack. Okay, and those are examples of this malware, like examples that has been done or has been experienced in the recent literature. And this is a taxonomy of this malware. So some of them are worms, some of them are Trojans, as you can see, and they run into different, operating systems. And you can see here Mirai and OMG are the ones that are related to Internet of Things. Okay, so this Mirai and OMG are related to IoT, and actually are engineered to hire large-scale number of devices to launch large-scale attacks. So these are two examples of this large-scale botnets, and this is actual coincidence here on the left-hand side, where a student in Rutgers University did this Mirai malware and was able to hire many number of devices, and he actually launched an attack on Rutgers University, leaving the faculty and the student on campus unable to access the outside internet for several days. And also they hacked or did a denial of service on the center authentication service, where they would fail to do course registration at critical times. Okay, so the idea here, he infects some devices, and these devices automatically infected other devices, and all of these are IoT devices, and they launched the attack. Also, like in the power grid, they say also that they can compromise power consuming IoT devices, and they can turn on and off them in the same time in a way to create an imbalance, and this imbalance can cause generator tripping and potentially large scale blackouts. Okay, so those are the problem statement here, and what is the challenges to secure this kind of networks. So like in the regular internet, in the how should I say, in the cyber world, we usually have a clear boundary between legitimate and illegitimate traffic, between secure and insecure domain, where we can actually put firewalls and can put security servers to monitor the traffic and see what is legitimate to pass and what's illegitimate to block. Okay, for example, here in KFUM, we have the firewalls. As long as you are inside KFUPM, you have all the privileges. But if you want to go outside KFUPM, you cannot just get these privileges. You have to have, like you go through like tunnels and, this VPN and so on and so forth. So we know what is legitimate traffic, what is illegitimate traffic. So when you are outside, you need more authentication and so on and so forth. But now in this wireless, like IoT, Internet of Things, we don't have this clear boundary between what is, legitimate, what is illegitimate domain. Okay, we also have these devices are randomly located. We don't know where they are. We have a wireless medium which is of broadcast nature, so you can get the infection from anywhere. Okay, we have massive number of devices, and we cannot, install patches and install malware, anti-malware programs in all of these devices due to, cost limitation for licensing, complexity, energy, and computational power. So the solution approach is to use graph theory to model the wireless network. So we can model the connectivity of the devices using graph theory, and then we can use percolation theory to study the malware diffusion. So each of these points in the graph can, can be susceptible, infected, recovered according to some engineering schemes. So we can then make this graph and this percolation theory account for the wireless communication kind of intrinsic features, and then we can study the malware diffusion and recovery and infection. And also we can devise some solutions. For example, here, one of the solutions that we have proposed is the spatial firewalls. And the question we asked is like this. So now if the hacker can infect some of the devices, can we have the same idea of firewalls that stop, like the virus from spreading more, and we get this quarantine? And this is, as you have seen this in the COVID-19. The same thing happened where we have lockdowns, so that if a virus initiated in some region, it's not effectively, transferred to another region, like the borders of the countries have been closed and so on and so forth. So how can we do this spatial quarantine? And this is one of the questions that we asked, and we used actually our background as wireless engineers to do this. And this will account for the geometry of the network, their wireless communication capabilities, and so on and so forth. And this is what we have, one of the solutions. So this is the firewalls. So we will hire some devices. These devices will have anti-malware programs to monitor the traffic and look for malwares. And the question, how many of them do we need to install, and where should we install them? And you can see here there are different, installation and techniques for the same number. And you can see here this red devices are the infected ones, and the green devices are protect regions or the firewalls, and the gray one are the susceptible one. And you can see that the malware can diffuse in the first 3 scenarios, and the last scenario where we add our background as wireless engineers, and take care of the wireless communication aspects for the malware diffusion. We're able to stop this malware from infiltration to large number of devices, and we're able to quarantine a small region. And then we can seek help from, other colleagues, as in the security department, in the IT department, to deal with this malware. But what we have done now, we have confined it to a small area, and we have stopped or disabled this adversary to get control of a large number of botnets that can enable him to make a catastrophic or a large-scale attack. This is one of the results that we have shown, that we can actually mathematically prove, that the network is immune to malware epidemics. So this is the intensity of devices, and this is the intensity of firewalls. So when the intensity of devices is small, actually the network is immune to malware epidemics because they don't have connectivity, sufficient connectivity to go through large number of devices. But when we start having massive number of devices, like we'll have in 5G and 6G, then it is susceptible to this malware epidemic. So we have to install firewalls according to what we have advised, so that we eliminate the risk. So this is the risk when we have insufficient firewall, and this is now we have safeguarding, and we can do this mathematically, and can we prove it, and we can help, as you said, other colleagues to sustain the network. And those are the points where the epidemics are stopped. This is the firewall intensity, and this is the portion of infected devices, and we can decrease the portion of infected devices by adding more firewalls. So we can control the cluster size of the amount of users or devices that can be infected. But at this point, malware is prohibited by physics and mathematics. And this concludes my talks. Thank you so much. And if there are questions, I'm not sure if I'm actually surpassed my time.
Thank you. Thank you very much, Dr. Hesham. You are just on time, but we don't have much time for question. We'll take one question if there is any question, or if you can leave your questions in the Q&A box.
That's up to you.
Or later on. Okay, so if no question, I will introduce our next speaker. Our next speaker is our Professor Salam Zummo. Dr. Salam Zummo graduated from our university. He's an alumni of KFUPM, but he got his PhD from Michigan, University of Michigan, in June 2003, and he served as the Dean of KFUPM Graduate School from 2008 till 2020. He is currently a professor in EE department in KFUPM, and a member of the Interdisciplinary Research Center of Communication and Sensing, Communication Systems and Sensing. Dr. Zummo has many awards, and he received the award for outstanding contribution to education in 2016, and the KFUPM Excellence in Research Award for the years 2012 and 2019. He got the Best Research Project Award in 2016. He has 16 patents, and he has more than 200 papers published in reputable journals and conference proceedings. Dr. Zummo interests include applications of artificial intelligence in signal processing and wireless communication. He will be today talking about 6G and AI, the next revolution. So I will give him the floor. Dr. Zummo, the floor is yours.
Assalamu alaikum. Thank you very much for having me today. I really thank the organizers. Do you see the slides?
Yes, yes.
Great. So today, inshallah, we'll talk about 6G and the artificial intelligence, the next revolution. I will start off by, okay, it's not working. Give me 1 second. How to remove the annotate, Doctor?
You can click on the presentation. It is not in the presentation mode. You can click on the cup.
I'm stuck with the annotate. I don't know how to remove it.
You can just press escape, Doctor. Press escape.
Escape, okay.
Yeah.
Great. So now, sorry for that. So I'll start with a big picture about the Industry 4.0. So we started with the first industrial revolution started back in several centuries ago with the steam engine invention, and then the electricity came with the second revolution, where basically manufacturing started to spread around the world, and goods became cheaper, and the industry started to increase all over the world. And then the third revolution started with the invention of the computer and spread with the internet, where basically information exchange started to become more and more across the world. Now, the fourth revolution is about the intelligence use of information. So if you look at the different applications of Industry 4.0, from autonomous robots to big data and analytics, augmented reality, and others, they all share two words, basically, intelligence and connectivity. So all of them they require intelligence use of information, and they require high density and require a lot of connectivity. So if we look at artificial intelligence, what artificial intelligence is, if you look at the formal definition, is the ability for machines to perform tasks that are normally requiring human intelligence, such as perception, recognition, decision-making, and eventually consensus. However, if we look at the connectivity, let's look at 6G. Some people define 6G as a smarter generation that fuses wireless and AI to provide dense and diverse and extended dynamic connectivity. So combining these two one of them should enable the other. What we'll try to argue today is how 6G will enable the different applications that the Industry 4.0 aspires for, which are mainly artificial intelligence based, and how AI will enable 6G to provide such dense, diverse, and extended dynamic connectivity. So today I will very quickly go over the evolution of the different generations, and then the 5G status and why is not enough to serve the Industry 4.0, and then how 6G will enable the AI applications, and the different enabled technologies that 6G will be using, and then how AI will enable 6G to make it smarter generation than previous ones, and then some examples of utilizing AI technology in wireless communication. So we know everybody is familiar with such a graph where basically first and second generation started some time ago, where the focus was the voice, and then 3G started with the internet invention and expanded into 4G, where the applications, where the smartphones started to provide or utilize a lot of data, consume a lot of data, high traffic data. And then 5G just 1 or 2 years ago started to roll off in the world, with the vision to have service for massive broadband and Internet of Things. Now, 6G is the vision is to have fully digital and connected world using new technologies that never existed before. So 5G, if we look at the current status, it is the first generation that provides 3 different set of services. The first one is the enhanced mobile broadband, where the capacity enhancement is the focus, and it basically the idea here is to provide high data rate, much higher than the 4G used to provide. The second application or the service provided by 5G is the massive machine type communication, where it connects massive number of devices together, and the main application here is IoT, Internet of Things. And the last one, or the third one, is the ultra reliable low latency communication, which is basically mainly for providing low latency service at a high reliability, and this is mainly for mission critical applications. What are the different issues in 5G that makes it not enough to provide the required services that 6G aspires for? First of all, that there are many applications that will emerge in the future that require a mixture of these services, not necessarily only the 3 services that are provided here, as well as these applications will require much higher specifications. For example, we are talking about in the enhanced mobile broadband, we are talking about a transmission rate of 1 terahertz, much higher than the current 5G aspires for. Similarly, for the ultra reliable and low latency and the massiveness. In terms of density, we are talking about almost 100 nodes for every cubic meter, while basically currently the 5G talking about 10 devices within 1 meter square. So you will require new KPIs to be supported by 5G, and also it lacks the intelligence. It lacks, the integration with satellite, UAV, and other networks that exist currently. The 5G or the previous generations, they are only terrestrial, and they don't integrate with the different networks. Basically, 6G aspires to connect these to provide 3D coverage, integration of sensing and localization, as well as it lacks the intelligence to support complex and dense and diverse heterogeneous networks. So if we look at the different applications, for example, massive scale communication and others, you will see that they need different set of KPIs, like a throughput, range, latency, reliability. Different applications require different sets. So limiting them to only 3 different services, the EMBB, the ultra reliable low latency, and the massive connected devices is not enough. And because of that, basically 6G is supposed or envisioned to provide multiple services, a combination of these 3 services, where basically you can combine ultra reliable with latency and at the same time high data rate, or massive connectivity with at the same time ultra reliability, and so on. And at the same time, every one of these will require extreme requirements, like extremely ultra reliable, extremely low latency, like for example the 1 millisecond range, extreme high data rate, like in 1 tera or 100 or several hundreds of gigabits per second. So if we look at the 5G compared to the 6G, the peak data rate, for example, in 5G is 10 giga. We are talking about 6G going to or reaching to 1 terabit per second. The end-to-end latency much smaller than in 5G, 0.1 millisecond, and this is extremely small compared to an end-to-end within a network. And node density is much higher, as well as reliability. One outage in one out of 1 million outage, and the coverage should cover the land, sky, and the sea, basically the whole Earth. Now, 6G will be able to help AI applications by providing the connectivity needed for different applications to provide ubiquitous intelligence, such as, for example, you can see here different examples that have been put to illustrate that the 6G is envisioned to provide much more applications than the current 5G provides. For example, one of the very important examples that people are talking about is the cyber space to physical space interaction, where the physical space is being replicated to a cyberspace fully, like a digital twin of it. And in this case, all the information regarding humans, things, and events are put into the cyberspace, where basically data are acquired or analyzed, like using big data and AI. And then you can do many experiments in the cyberspace with almost zero cost. Like, for example, if you are building a designing a building, you can do too many changes within the cyberspace without even having to pay anything in the physical space. And in this case, basically, the cyberspace will be used to forecast new knowledge or discover and find the different scenarios. And hence, after that, the action will be going to the physical space for using actuators or others to provide the action needed in the physical space. As you can see, all this requires huge data rate and different specifications like low latency and high reliability in the uplink and the downlink. So it's not anymore like in 5G where the downlink is the main focus. Here, even in 6G, we are talking about high data rate at the uplink as well as the downlink. Now, what are the different enabling technologies in 6G? One of them is one of the most important ones is the use of ultra high frequency communication. Now, currently, in the first several generations, we were bound to the gigahertz communication, where basically we're used to use up to 2 or 3 gigahertz frequency. In the 5G, they started to use the millimeter wave, around up to 50 gigahertz frequency. In the 6G, we are talking about utilizing in the frequencies in the range of terahertz, which is basically just right at the boundary between the photonics and the electronics. So higher than the terahertz, several terahertz, we talk about the emergence of the light and the photonics. And of course, also in addition to the terahertz, we'll talk about using the visible light communication as well as the higher range of the millimeter waves. Now, the advantage of using such high high frequency range or band is, first of all, having higher carrier frequency means that you can have much higher bandwidth compared to the previous generations, as well as having higher data, having high frequency will allow you to have new energy efficiency regimes, to operate in new energy efficiency regimes, as well as there will be different cost versus size rules. We are almost verging it through the photonics side, and it has basically different rules than the electronics side. Classical theory is different than quantum theory. And of course, it will have its own challenges where the propagation loss will be larger, the penetration loss is an issue, as well as the molecular absorption. So basically, you will talk about probably the health of the human being might be affected if this is not engineered very well. Of course, looking at the high frequencies, you will allow for more power efficiency and as well as higher, more coverage, because you will, in this case, you will have extreme coverage, including the networks existing currently. The second enabling technology is the intelligent radio, where if you look at the previous generations, we used to use a radio that uses only one technology, for example, FDMA, TDMA, CDMA, whatever, OFDM, and so on. Now in 5G, they started to use, of course, it's mainly focused on OFDM and millimeter wave with massive MIMO. But in 6G, we are talking about different combinations of these, including the OFDM, the non-orthogonal multiple axis, as well as the centimeter, millimeter wave, and terahertz frequencies. So the radio here needs to be intelligent, deconfigurable enough to provide support for diverse capabilities and requirements. And mainly it will be AI powered. Among the enabling technologies is the large intelligent services, where basically you will have large services acting like antennas with a passive or not, with a passive or active antennas to relay to help in relaying and delivering information to users. Of course, having large intelligent services will require will be basically based on new physics or the new manufacturing process to allow such very small size antennas to work and to be reconfigurable at the same time. Of course, this will give us ultra-massive MIMO, because the number of antenna elements will be extremely large, not only large. and it will also, which will allow for extremely higher data rate. Of course, it will require more complicated signal processing that is most likely will be powered by artificial intelligence, as we'll talk in a minute. Of course, cell-free networks will be part of the implementation of 6G, because it will allow for more or higher sum rate at the network level. Of course, it will look like a virtual ultra massive MIMO. In addition to that, smart and dense beamforming, where basically all these antennas in the large intelligent services will also provide beamforming to allow to maximize the signal to noise ratio for specific users. Of course, looking at the network level, the network will not only, as I mentioned, it will be only the ground networks that we used to have in 5G, where device to device, vehicle to vehicle. No, you will have underwater and sea networks. You will have space networks and air networks, where satellites, low orbiting satellites, HABs, which are the basically pseudo satellites, as well as the UAVs, are expected to be connected to within the 6G network. Of course, this all will give us the first time communication in the sky, and which will allow for higher for the wider coverage, much wider coverage than what we used to have, which will allow for new different applications and new different services like intelligent architecture, disaster and rescue, and so on. Of course, all these will require optimization or resource allocation, and most likely this all will be powered by artificial intelligence. So now, what is the main part of if we look at artificial intelligence, the main classification of artificial intelligence is of course, we are talking mainly about machine learning here, and machine learning can be by supervised learning or unsupervised learning, or reinforcement learning, where in reinforcement learning, you allow certain agents to learn the environment and to decide what actions should be taken according to certain rewards. So, for example, if the reward is maximizing the sum rate, then the agent will be trained so that it maximizes the sum rate, and so on, or minimizing the outage, and so on. Among these is the deep learning, the share point between all these different techniques with deep learning, where neural networks or convolutional neural networks or whatever neural networks can be used to implement one of these networks. So the good thing about AI is, although it requires sometimes to be trained, however, once you invest in the training, the interest time is almost instant. So basically, it becomes more handy in the real time application, where basically 6G is mostly about. So why in 6G? Why do we need AI in 6G? Because, as I mentioned, we need to have intelligent air interface because of the too much complexity in the network and the channel modeling, and the high or rich interference environments that we are living in. Also, we need to look at the physical layer and the different layers and look at the holistic approach for designing them. Integration of sensing and localization, as well as for extreme energy efficiency. And from the network architecture, you need to provide different requirements for quality of service and quality of experience, as well as diverse networks, as you mentioned. So if we look at only one simple example, the physical layer, we used to have a single antenna transmitter where an encoder, modulator, and transmitter, and then followed as a receiver by the opposite function. In this case, we used to have closed form analysis with optimal solution. And then things got complicated a little bit with MIMO and OFDM, where still we used to have closed form analysis with complex implementation. After that came basically the massive MIMO, the NOMA, and other technologies where closed form solution was impossible. However, a synthetic analysis was there, and we used to have suboptimal solutions. In the sixth generation system, we are talking about massive MIMO, ultra high, ultra wideband, or terahertz frequencies. So basically, models do not exist yet, and the analysis of such models become extremely difficult. And because of that, we will all resort to mainly AI-based solutions, where basically the transmitter and the receiver will be kind of neural network or something powered by deep learning. Now, if we look at the different
Dr. Salam, the voice is not clear.
Okay. Is it okay now? Better?
It's better.
Okay. So if we look at the different areas in which 6G basically requires help of the AI, we can see that in advanced radio, in the intelligent traffic control management, for example, let me focus on the physical layer. We have the channel estimation, the modulation, we will use different frequencies and different transmission rates and different requirements. So we will use different modulation techniques, different coding, and so on. And because of that, you need to have recognition of the modulation scheme of the receiver, ability to select and adapt the different modulation and coding, and allow for channel estimation and detection in a very complex environment and the frequent and interference-rich environment. And so all this requires much more sophistication than what we used to do in closed-form solutions that we used to have. So, for example, the intelligent, the transmitter, the receiver, as well, all of them require end-to-end optimization from the physical rail interface to the network itself. Of course, we will need also to have edge AI, where basically AI will be also allowed not only at the central location or the central network or the core network. You will also need to have it at the edge to have faster, so to find the solution faster and to implement it. So very quickly, some examples on application of deep reinforcement learning in different networks, in wireless networks. This slide shows basically the work of Ahmed Bahdar from KFUPM, where basically he considered two cell-free networks, DLC and RF, and he tried to look at the user association problem, where basically what is the best strategy to associate different users to different networks. And he applied different classical approaches, among them the iterative. And you can see that at 14 number of users, 14, we can achieve almost around 4,000 megabits per second sum rate. Now, if we employ that reinforcement learning, deep reinforcement learning, we can achieve almost very similar, 400, slightly larger than 4,000 megabits per second of head using deep learning. Of course, not to mention here that the inference time is much faster than the previous or the classical approaches. Another example is using UAVs for the laying, where basically the problem here is to select the laying based on the level of harvested energy. So the higher the harvested energy by the UAV, you will select that UAV to harvest. And the problem is to optimize the path of the UAV while it's moving, so that you maximize the throughput. And you can see that here we are plotting the SNR.
Salam, we don't have much time.
Yeah, I will close in 1 minute. We can see that here the deep learning approaches the deep learning approach provides much faster, higher SNR, as I mentioned again, at much faster inference rate. I will go just skip to the conclusion. As you can see here that in order to enable the Industry 4.0, you need to have 6G as well as AI, the connectivity and the smartness or intelligence. And we can see that 6G will enable AI applications by providing dense and diverse connectivity to create different opportunities, new opportunities to enhance society and economy, with many examples or application examples like mixed reality, digital twins, and holographic presence, and so on. By achieving new KPIs for mixed combination of services, the high data rate, the high reliability, and the massive connectivity, and so mixed combination of these, as well as extreme KPI services, extreme service KPIs. And also AI will enable 6G implementation by enabling intelligent and diverse networks, by using the big data and AI to predict and enhance the user experience, and to better design end-to-end communication at the different layers of the 6G network. By this, I thank you very much for your listening, and sorry for the start of the presentation. Thank you very much.
Thank you very much, Professor Salam. Our third speaker is Professor Muhammad Moinuddin. He is MSc and PhD from King Fahd University in 2001 and 2006, respectively. He joined the ECE of King Abdulaziz University in 2013 as assistant professor, where he was promoted to the associate professor in 2015. And since 2019, he's a full professor in the university. He is also associated with the Center of Excellence in Intelligent Engineering Systems. His research interests are in signal processing, adaptive filtering, wireless communication, neural network, and machine learning. He's mainly interested in the application of signal processing and artificial intelligence in various fields of engineering. Professor Moinuddin has approximately 100 peer-reviewed journal papers and conference publications. He has 5 patents and 5 book chapters. So please join me to welcome Professor Muhammad Moinuddin, and the floor is his for presenting his talk about statistical beamforming, a solution with higher spectral efficiency for future rural wireless communication. Dr. Muhammad.
Thank you very much, Dr. Zudari. Assalamu alaikum to all. It's my honor to be part of this panel, and I'm very glad to be part of this team. Inshallah, I will be presenting today statistical beamforming as a solution for future wireless communication. The content of my talk is as follows. We have introduction in the beginning, what is beamforming, what are the conventional techniques used in the beamforming. Then we go for the challenges for 6G and motivation for the proposed solution, which we are discussing in this talk. And then we see the approach we apply for characterizing outage probability in order to use for the beamforming design, few applications which we have worked so far, and or the future plan which we are working on it. And then we conclude our presentation, inshallah. So what is beamforming? In simple words, the task of beamforming is to manage the radio frequency signal in a way that it will be directed towards a specific direction. So instead of sending a signal in all direction or sending the resources in all the direction, we can direct the beam or the signal is sent to a particular direction where we want to send the signal towards a specific user. So in this way, we can utilize the energy and the resources more efficiently. Different kinds of techniques are used: analog beamforming, digital beamforming, hybrid beamforming. In very simple words, analog beamforming is used in the RF domain, where the signal is the signal beam is controlled by phase shifter circuits, where the amplitude and phase are controlled by analog circuits, and these are transmit to the multiple antennas. In digital beamforming, we worked on the digital converted signal. So from analog to digital conversion, once it is done, there's a circuits which are used to assign amplitude and phase in a way that these could be in a specific direction. In other words, the beamforming can also be considered as a spatial filtering. So we are applying a kind of a spatial filtering in order to achieve the beam in a certain direction with certain magnitude. In conventional beamforming techniques, like for example, if you see this basic model of 2x2 system, where we have base station 1 and 2, we have 2 mobile stations, we are receiving signal as a composite signal from the 2 transmitters, and each signal is transmitted through some beam formed signal. So WJK is representing the beam vectors or the beam coefficients which are assigned to a specific user, in this case the user 1 and user 2. So these signal, when are transmitted and received at the receiver side, it has the effect of channel as well as the adaptive noise. The task of the beamforming design is to design a solution of these beam vectors such that we can compensate or we can mitigate the effect of channel as well as the additive noise effect. Most common or most popular in this field are the maximum ratio combining or maximum ratio transmission and zero forcing transmission. If you can see, these are the well-known techniques which are based on the knowledge of channel. So what is usually done in practice? Pilot transmission is provided to the system, where based on pilot transmission, these channels are estimated. So these in the uplink communication, the channels are estimated, and these channels, instantaneous information are then utilized to implement these methods. Other than these methods, there are other methods like adaptive beamforming techniques, which are based on the signal received without knowing the channel, but they are not as much efficient as these channel-based techniques. The challenge in what is the challenge in the existing method and what we are planning for future? So let's go for 6G. When we talk about 6G, before going to 6G, let's see one of the challenge in estimating the channel, because up till in 5G, like in massive MIMO, it is assumed that we can implement time division duplexing, and we have coherence time during uplink and downlink. The whole time is within the coherence time, and for this reason, the channel reciprocity will exist. And if the channel reciprocity exists, it means if we estimate the channel in the uplink, the same channel can be utilized at the downlink, and this will not require further pilot transmission at the downlink to estimate the channel. So what is the conclusion? That in existing massive MIMO, time division duplexing with the aid of coherence time availability, coherence time assumption, you can say, that we can estimate the channel in the uplink, and we can utilize the same channel estimate through feedback at the downlink, and we do not need to estimate the channel again. So for this reason, instantaneous channel estimates are sufficient only through the uplink. There's no need to estimate the channel at the downlink. But practically, this is not true if we are using frequency division duplexing, or if we are not having the coherence time enough that is sufficient for both uplink and downlink. So if the channel is changing fast, no more same channel we can experience in the downlink. So there's a need to estimate the channel again in the downlink. But the problem is that if we want to estimate the channel in the downlink, it will cost a lot of overhead, and the feedback will result in a large overhead. This will reduce the spectrum spectral efficiency of the overall system. So this is a very big challenge. And if you see a vision of 6G, in the 6G, if you see the spectra which they are proposing, we can go for millimeter wave, we can go for terahertz. So these frequency range are very high frequency range, and in this one, the channel characteristics are changing so fast that we cannot avail coherence time both in uplink and downlink. And you can see another challenge in the 6G spectrum efficiency. What is proposed in 5G and what we are requiring in 6G is far ahead, is almost greater than 3 times. So in summary, I want to give a quote from this recent paper, one of the recent paper published in 2019, that if we are going to implement in real time the beamforming for millimeter wave or terahertz frequency range signals, the problem is that we cannot have the same coherence time for both uplink and downlink, and even we are facing shorter channel coherence time even for a fixed Doppler spread. And there are other than this, there are some other issues like higher phase noise and some other constraints. But most importantly, the coherence time assumption cannot be utilized even in the time division duplexing, and in the frequency division duplexing, there's no choice of coherence time, the same coherence time. So what is the bottleneck? We need to do uplink and downlink estimation separately, and this causes a lot of overhead in the system, and it will reduce the spectrum efficiency. So what is, let me summarize what people have done so far. People have used multiple antenna-based system for improving the quality of service, but usually they are requiring instantaneous channel status information, which assumes that we have coherence channel coherence time exists for both uplink and downlink, and the uplink estimation is sufficient to be utilized at the downlink. And But in practical scenario, as I mentioned, and in the 6G requirement for millimeter wave and terahertz, we cannot guarantee the channel coherence time, and we cannot avail both uplink and downlink, same channel instantaneous estimate. So we cannot utilize instantaneous CSI. So so one of the possible solution is to go for statistical CSI, and people have used statistical CSI as a key performance indicator, such as outage probability or ergodic capacity and some other performance measures in order to design the beamforming solution. However, the problem is that in designing these or in achieving these key performance indicators, people have used certain assumptions. Even with the simple channel as Gaussian, they need to assume uncorrelated channel or independence, or there's many assumptions people have used in the reference, few references I mentioned here, to design the key performance indicator like outage probability and ergodic capacity. So these are the limitations in the existing work. What we are proposing, what we have investigated so far, we, instead of going to instantaneous channel information, we are also proposing to use statistical channel state information. And for that one, we are going to design or drive expressions for key performance indicators like outage probability and ergodic capacity by using more realistic approach for characterizing these random variables. We have used an approach called indefinite quadratic forms, in which the random variables, we do not need to assume certain strong assumptions like uncorrelatedness and independence. These kind of assumptions we can omit. So, for example, if you see in the screen, this Y1, Y2, Y3, these are some forms of indefinite quadratic form where H is a Gaussian, complex Gaussian random variable weighted by certain matrices A and B here. And these can be indefinite form, and we can have ratio also. As you can see, Y2 and Y3 are the ratio forms for indefinite quadratic form. How to characterize these indefinite quadratic forms? We came up with a very good solution we published in 2016. Based on these techniques, we tried to develop beamforming solution. In short, our approach relies on characterizing these multidimensional Gaussian random variable function of this indefinite quadratic form. As you can see here, this H square weighted by A, if we want to characterize what is the probability, it is less than certain quantity. We can write this probability as a multidimensional integral, and this multidimensional integral can be expressed in terms of probability density function, multidimensional probability density function with the aid of unit step function. The detailed procedure can be found in our research papers, but I'm not going to the detail how we drive it. But we have a closed form solution how to find the closed form solution for such integral. So what we have used in our application, for example, in one of the work we work on MIMO system in which both transmitter and receiver are equipped with multiple antennas, and both transmitter and receiver are employing beamforming. And we want to design these beamforming without having instantaneous channel information. So we are looking for some channel state information as a key performance indicator, which can be outage probability, can be ergodic capacity, can be leakage rate. And what are the design tasks? We want to design transmit beamforming as well as the receive beamforming. So in this paper, which we published in 2020, we designed using the outage probability, these beamforming solution. Just to give you some glimpse that what we drive for more general scenario of having both transmit and receive beamforming. We drive the outage probability in closed form using the indefinite quadratic form characterization as a function of both transmit and receive beamforming and threshold value of the outage power. And then we cast the problem as a multi-objective optimization problem. And we, in this work, we developed two different methods to solve this problem. One was a sub-optimum problem in which instead of going to solve the actual non-convex nonlinear problem of optimizing the outage probability, we transformed to a sub-optimum problem, and using the generalized Rayleigh quotient approach, we found a closed form solution. Other approach, so this was the first solution, and the second solution was we went to the heuristic approach to find the solution for this non-convex problem using state-of-the-art techniques like sequential quadratic programming, in which we transform the non-convex problem to a convex sub-optimum problem, and we use analytical iterative solutions to achieve the result. Just to give you some results, that for different scenarios with different antenna size and with different system parameters, we have investigated the results of these transmit beamforming and also the receive beamforming for different system parameters, and we have compared with the state-of-the-art existing techniques, and we can see that we have achieved better performance in terms of outage probability in this task. And we have also investigated the MISO scenario instead of MIMO, and we have also published this work. This is one of the PhD student in King Abdulaziz. Dr. Tareq was also as a co-supervisor there. And one work we investigated in MIMO system, in which we implement like a beamforming as like a spatio-temporal filtering solution. So in that one also we implemented this indefinite quadratic form based approach to find the solution by minimizing the outage probability, and we came to a solution which is better than the existing solutions. And some other applications, like recently we explored how to use ergodic capacity, both leakage and the ergodic capacity of the SINR and the leakage SNR. We have derived closed form solution, and these closed form solutions for both leakage and instantaneous SINR based ergodic capacity, we came to closed form solution, and those closed form solutions are then utilized to optimize the beam vectors for the transmitter and the receive system. So we have implemented this system. You can see some of the solutions in this work. We have recently published in 2021 this work. And this is another application, cooperative multi-user MISO NOMA system. As you know, the NOMA is one of the candidates in the 6G, and also it is a promising solution for better spectral efficiency. And we utilize again here the beamforming, where we utilize again outage probability based on our approach. Some results are there. I will skip the details. On some ongoing works, what we are doing right now, one work we are doing right now with our collaborators on cooperative multi-user MIMO NOMA system, in which we are again designing key performance indicators like outage and capacity in order to design the beamforming solution, in which the cooperation is done through the near and far users, and we are trying to optimize this cooperation by the beamforming solution. Another work which we currently are doing is on the power domain NOMA, where the users are grouped in pairs based on near and far user power allocation. So in this one also, the task is that in conventional techniques, successive interference cancellation is done, but with the assumption that we have the perfect knowledge of channel. And again, this requires the pilots-based channel transmission. And as I highlighted in the beginning, that it is depending on channel coherence time, which is no more practical in terahertz communication or millimeter wave communication. So we are proposing again statistical CSI based solution in this one. What we can explore in future, there are many applications like intelligent reflecting surface based antenna system, where the beam also again required to design, and this can be future arena to work on it. And also There are cell-free networks where people are exploring for future wireless communication. And also there, the beam is designed, but the constraints are different compared to the cellular network. So there, the design parameters and the constraint scenario are different. So we can also explore such scenario. So these are the few future directions which can explore. In concluding remarks, what I can say that statistical beamforming can be a very good solution as the requirement of 6G millimeter wave and terahertz communication required the higher spectral efficiency without having channel coherence time assumption valid. So this can be a better solution in future wireless communication. The IQF approach, which we have explored so far, can provide better characterization of KPIs, which we have been using, and we can explore more KPIs in future. And there are some future directions which I have mentioned, which we can explore. So I'm done with my presentation. Thank you very much. And these are some references which you can see. So inshallah, questions.
Thank you very much, Professor Moinuddin. And before giving the floor to our next guest speaker, Professor Tareq AlNaffouri, just we'll take one or two questions if there is any question. Okay, so please, before the end of the speech of any presenter, you can write your questions in the Q&A, or you can raise your hand and we give you the floor. So our next speaker is Professor Tareq AlNaffouri. He is also an alumni of KFUPM. Professor AlNaffouri is in the electrical and computer engineering in KAUST, and he is the principal investigator of the information system lab. He is also an active member of the Sensor Initiative, SI, at KAUST. Dr. AlNaffouri got his PhD from Stanford University in 2004. He was a visiting scholar at California Institute of Technology in 2005, and also during the summers of 2006, 2008. He was a Fulbright scholar at the University of Southern California in 2008. And in 2012, he joined the KAUST, where he is currently a full professor. Dr. AlNaffouri's research interest is in the adaptive and sparse and statistical signal processing and their application. His research also extends to the design and analysis of wireless network. I will give the floor to Professor Tareq AlNaffouri for giving his talk about towards the convergence of communications, localization, sensing, and imaging in 6G. The floor is yours, Dr. Tareq.
Thank you, Dr. Okay. Yeah. Thank you, Dr. Malik, for your kind introduction. Can you see the slides?
Yes.
Okay, very good. So first of all, I'd like to thank the esteemed organizers, Dr. Abdullah Ahmadi, Dr. Alim Gable, Dr. Malik Zaidouri, the KFUPM for inviting me and hosting this very interesting event. Bismillah ar-Rahman ar-Rahim. So, assalamu alaikum, everyone. So basically, like, this talk is about the convergence of communication, localization, or the sensing and imaging inter-system systems. The convergence of various services that basically are promised, like, in 6G, and in particular 6G that's based on terahertz. This work is basically a joint work with Professor Salam AlOuini, and it's led by our joint postdoc, Dr. Hadi Sariyuddin. So basically, the outline of the talk is basically what I'm going to talk about terahertz, its challenges, and how these challenges enable various services, and how these services have to, which are right now are kind of like separate services, how they have to converge in a terahertz scenario. So the speakers have already, the esteemed speakers have already talked about, like, you know, the growth in the applications and the data rates that are needed for these applications. So, for example, we have an exponential growth in the internet traffic, and this is always has been pushing the capacity limits of the wireless networks. And for that reason, this is why we actually continue to see, you know, evolution of generations from the first generation all the way to the 5th generation that was, like, you know, rolled out last year. And so now, like, you know, with new applications that are being envisioned, like, for example, e-health, extended reality, autonomous driving, the applications that are enabled by AI, all of these kind of, like, you know, are going to be, like, you know, even more data hungry. They're going to be, like, more kind of susceptible to, like, you know, latency. And so that's why, you know, the next people have been working about, you know, on the sixth generation. So here is the good news. The good news is that actually in the past, like, you know, all the 5 generations have barely used like 100 gigahertz of the existing spectrum, while the full terahertz spectrum, which extends essentially to 10 terahertz, is available. Now we cannot use all of it, but actually we can. At least we know that, like, channel measurements suggest that we can use, say, up to 900 gigahertz of spectrum, which gives us, like, 9 times the spectrum that we have been so far using for communications. And that in turn kind of, like, you know, motivates new applications that we can, like, you know, rely on. Say, for example, macro scale communications, satellite communications, all the way to body-centric networks and interchip communications. Now, that not only provides opportunities for communication, but actually for other services. For example, the terahertz will enable actually very accurate localization, system level accuracy, thanks to the tiny wavelengths and the narrow beams that we actually we have. The other thing also is that it will, because of the high bandwidth, we have a very high delay resolution, and so ranging will be much more accurate. So both the angular localization and and ranging will be better, and that will result in system meter level accuracy. Not only are we able to actually localize, but we can actually have environmental maps, similar to what the LiDAR does. And you know, as opposed to what happens, you know, in previous generation, where localization is a service, now localization becomes a prerequisite, because the footprint of the devices, when you are talking about terahertz, becomes much smaller. So basically, like, you know, the message that I'm going to like present is terahertz is going to enable many more services. These services have to there are lots of challenges, but also these challenges are sometimes opportunities. And what you're gonna see is that eventually these services have to kind of converge in a way that I'm gonna explain in a minute. Now, of course, some people would say, why terahertz? Why don't we just stick to millimeter wave, or, for example, visible light communication? Well, in addition to the additional bandwidth and data rate that we can get, for example, terahertz will have higher directionality. It will have smaller footprint, so your devices will be even smaller. You'll be because of the narrow beam width, the narrow wavelengths, you have, like, you know, resilient to eavesdropping. We also have some advantages over, like, visible light communication. For example, we're less affected by ambient light. We can better exploit the reflections. We can make use of array processing. So all of these kind of, like, you know, make terahertz. These are some of the advantages of terahertz over millimeter wave and visible light. But as you're gonna see, actually, they need to complement each other. We cannot just rely on one technology. So how do we go there? So we expect in 2030, hopefully, to be like, rolling out 6G. But there are some challenges. The first challenge is basically devices. Okay, what devices, what transmitters and receivers can operate at such high frequencies? Now, this is not our area. I mean, not my area, and I'm assuming it's also not the area of the esteemed speakers. But there are several contenders. You can have electronic solutions, photonic, hybrid solutions. Perhaps the most appealing is what's called plasmonic solutions based on graphene. And this is kind of like allow us to kind of to have like a huge number of a massive number of antennas, and also it's highly configurable. So this is the first channel, devices. The hope is that they will be ready by the time we want to roll out 6G. The second challenge is what comes between the transmitter and the receiver, the channel. Okay, this is where us communication system engineers are interested in. This is important for standards, for things at the physical layer, things at the MAC layer, and even at the hardware layer. So this is why we need the channel modeling. So what are some of the things we care about? Say the path loss, the large and small scale fading, and even blockage, because as you're going to see, actually blockage is a big issue in terahertz. So this brings me to one of the main challenges in the channel of terahertz, which is basically the path loss. This figure shows you the path loss versus frequency. And as you can see, the path loss increases as we go in frequency, and also it increases with distance. So here we're varying distance between 10 centimeters and 100 meters. And you can see that the loss keeps increasing. What's more is actually we see these huge spikes in loss due to molecular absorption. So this is one of the main challenges for terahertz, or for the terahertz channel. Of course, we are interested in modeling other parameters of the channel, like the coherence, time and bandwidth, the channel correlation, the sparsity, etc. Now, to deal with the path loss, massive number of antennas is a must. We cannot rely on a single antenna because the output power of a single antenna is very limited. And also, like, you might have antennas with high power, but they are bulky. They cannot be used for our mobile devices. They might be used for backhaul links, but to be able to actually combat the path loss, the extreme path loss that we have in terahertz, we have to rely on massive number of antennas, and the beamforming gain that we get kind of allows us to deal with distances. So to give you just an idea of how, with massive number of antennas, we can deal with path loss, I'm showing you here the localization accuracy versus the number of antennas we employ. And I'm comparing it with millimeter wave. So what I'm doing is basically I am assuming that the physical footprint of the massive number of antenna remains the same. And I'm going to compare millimeter wave with terahertz. So this is the performance of millimeter wave in the solid black line. And as you can see, as I increase the number of antennas from 16 here, for example, all the way to 100, the accuracy keeps improving. Now, if I do the same thing for terahertz, the performance is not very good. However, since I have the same footprint, and since the wavelength in a terahertz is much smaller than than millimeter wave, what I can do is actually extend spread out these antennas and improve the performance. But now, since I have a much higher spacing, I can actually fill it up with more antennas, and that kind of can improve the performance beyond what millimeter wave has. So here I'm comparing things when I'm fixing the footprint and the power consumption. As you can see, because of the smaller bandwidth of terahertz, because of the smaller wavelength, so because of the higher bandwidth, we can see an improvement. So back to what I was talking about. What we want to do is we want to model the channel. There are several ways of modeling the channel, deterministic and statistical. I'm not going to go over that. But one thing we did in our groups, Professor Slim and my group, is basically to actually provide TerraMIMO, which is a channel simulator for ultra-massive MIMO terahertz communication. This simulator is already, the details are published in this paper and it's available on GitHub. And what we have here is 3D end-to-end channel modeling. We model various aspects like line of sight, non-line of sight, or line of sight dominated channels. We talk, for example, we model things like molecular absorption, which that I'm going to talk about, time variant channels. We're going to model like, planar and spherical wave propagation, misalignments, etc. And this basically, as I said, is available on GitHub. The MATLAB programs are accessible. You can change them if you like. If you prefer, there's a GUI that kind of like lets you control the parameters of what you want to simulate. And here are some sample results. For example, this is the same result I showed you before, the path loss versus frequency. Again, as you see the path gain, as you can see, gain decreases with distance and also decreases with frequency. In addition, the other thing that you can see is these valleys, okay, of gain, where you kind of essentially have no signal. So in the rest of the talk, I'm going to talk about around 4 challenges in terahertz. Now that we have modeled the channel, we can talk about 4 challenges in terahertz communication. And let me first start with what's represented here, which is basically the molecular absorption. So molecular absorption basically is the effect that various gaseous gases are available in the atmosphere, and the absorption that happens when the terahertz signals interact with these gases. And what happens is basically, as I said, basically you have a huge loss these gases, because of these gases, especially at large distances and at large frequencies. Now, how does this affect communication? Well, basically, it fragments the bandwidth that you have, the huge bandwidth you have, it fragments it. And you have to kind of rely on some form of hierarchical bandwidth modulation. It also affects localization, because now, you have to kind of figure out for targets that are at different distances, you have to allocate specific bandwidth for localization. However, that challenge is actually turns out to be very good for sensing. Why is that? Well, here, look at this figure. This figure shows you the spectral fingerprint of various substances, like, for example, chalk, aspirin, baking soda. And as you can see, the spectral fingerprints are different. Similarly, we have differing fingerprints for gases. So what that says is that the same terahertz signals that you are using for communication, you can actually use for sensing. And if you implement ultramassive MIMO at the transmitter and at the receiver, then you are able to sense these substances at a distance. So this kind of and you can do that at a fine resolution. So now what you can do is you can piggyback sensing on top of communication. And so we have this convergence of the 2 services. Now, a similar effect to molecular absorption is blockage. Blockage is basically what is well known is that signals at higher frequencies are more sensitive to blockages. Blockages which we don't worry about usually. Walls, humans, become problematic, and so we have to deal with it. So, for example, you have to place your access points at high altitudes. You have to deploy multiple access points. A single access point will not do. You have to actually take care about how to do user association, depending on do you associate to the nearest access point, or do you associate to a distant one, but that one that gives you a line of sight. Now it turns out actually blockage even happens outdoor. So, for example, it could be due to the devices themselves that exist in the environment, but actually it's affected by the atmosphere and the latitude. So, for example, here I'm showing you the coverage probability versus frequency. And what you see here is that the coverage in the summer is worse than the coverage in the winter. And the reason is that actually vapor or humidity is higher, has a higher concentration in the summer. Similarly, you can expect more coverage at a higher altitude where the density of gases is less. So blockage happens, you know, in both indoors and outdoors. Now, this is one thing that actually we worked on here at KAUST, actually in collaboration with and this is basically, this work is led by Dr. Noor Quzaiha. And what we did is basically kind of like, you know, one way of dealing with this challenge of blockage is that you have to have coexisting RF and terahertz wireless networks. So basically what you do is you have a finite number of access points. You give a delta. Delta of them will be the terahertz, and 1 minus delta will be the RF access points. And so we kind of like, you know, try to analyze the effect of blockage, as I said, of walls, like, you know, maybe like, you know, you might have cubicles, you might have also humans, which we kind of model like cylinders, and we try to model this effect and see what happens when we vary the number of terahertz access points. So this is the fraction of terahertz access points between 0 and 1, as expected. Let's start with the rate. As expected, the more terahertz access points you have, the higher the rate that you can get. However, the coverage gets affected. If you have more terahertz points and less RF points, eventually your coverage will be less because of the path loss, and so your quality of service will be affected from that aspect. So there should be a compromise between millimeter wave, say, and terahertz access points. They in a way complement each other. So I talked about molecular absorption, blockage. A related kind of like, you know, blockage scenario is misalignment. Sorry, is misalignment. And so basically what's happening here is because of the massive number of antennas we are employing, the beams you implement become very, very narrow. Now this has its advantages. You have less interference, so security is less an issue that Dr. Hesham talked about. You have a higher angular resolution, and so you have a better localization accuracy. Now the disadvantages is that actually the misalignment becomes an issue. So aligning the transmitter and the receiver becomes more and more difficult. And so link establishment, right? Establishing the link between the transmitter and the receiver becomes a problem. And you have a deafness issue. It's as if like the receiver does not hear the transmitter. And actually this gets exacerbated with movement. So if you have movement, then this becomes more of an issue. Here is this is some simulation that shows you the expected gain versus variance of antenna motion, or the speed of the motion of the antenna. So as you increase the speed, you expect the gain to kind of get lower. And also the misalignment, you expect it to have a higher effect at a distance. So the misalignment effect here, which is 20 meters, has a less effect than when it is for 100 meters. So what I want to say here is actually this shows you that localization is not a service on top of communication. It's actually a prerequisite, because unless you are able to align the transmitter and the receiver, and so basically you have to kind of dynamically track them. Unless you are able to do that, you cannot kind of establish communication. So you have localization and communication converging. Now, in this case, it turns out that actually the solution that I talked about that helped us with blockage, which is basically hybrid RF and terahertz solution might help. So if you can see here, for example, I'm showing you the coverage probability versus the effect of misalignment. As we increase the misalignment, we get hit actually in terms of the coverage probability. However, what's noticeable here is that, for example, this green line, for example, has a 60 degrees misalignment, which is huge, as compared to this line here, which is 20 degrees of misalignment. So why do we have better coverage? Well, the reason is that we're able to, when we have such a high misalignment, the user is associating with the RF base station as opposed to associating with the terahertz. So this hybrid use is actually in a way helping us to improve the the coverage probability in spite of excessive misalignment. So I talked about molecular absorption, blockage, misalignment. What that results in, if you think about it, it results in non-line of sight. So the non-line of sight phenomena becomes more important because of these three quote-unquote blocking effects. Now in the terahertz channel, we expect to have fewer non-line of sights. It's more like visible light communication. However, we do still have some non-line of sight transmissions, and that actually is helpful because it makes the MIMO channel less correlated. It's also helps us in localization. For example, I show you here in this figure localization that happens when I have between a base station here and user equipment here and several reflectors. And it turns out that what's happening is the following. The accuracy of localization in the vertical line versus the reflection coefficient of the non-line of sight, the more reflection I have, the higher the accuracy, so I have less errors. And the more reflections I have, the better the accuracy. So non-line of sight also is helpful for localization. However, that happens at the cost of increased complexity. Now, given the advantage of the non-line of sight, basically, now we can talk about artificially creating non-line of sight through the reflective intelligent surfaces that Dr. Salam and Dr. Moin talked about. So now here we have a transmitter, we have a receiver, and we have some reflectors, but we can actually place some artificial reflective surfaces that kind of help change the channel, help change the model of the channel. It will also help us because the MIMO technology that we're looking for is still not mature enough. So it helps us in communications, but also it helps us in localization because now I can have what's called around the corner localization. So here I'm showing you some simulation. Again, this is kind of all of this is part of a tutorial that we recently submitted, and it shows you the effect of localization accuracy versus number of elements in the reflective surfaces. And as you can see here, if I don't use any the reflecting surfaces, basically I don't gain. However, by using the reflecting surfaces and by actually using what's called adaptive beamforming, in the sense that I target some beams to the reflecting surface, and I target some beams towards the target itself, to the user equipment itself. So by using adaptive beamforming, we can actually improve the performance. The last point, or the last two challenges I want to talk about, is basically planar versus spherical wave models. In terahertz, because of the small field footprint and because of the small wavelengths, the regular assumption of having a planar wave model no more applies. And so if the transmitter is close enough to the receivers, you have to actually talk about a spherical wave propagation. Now this makes things more complicated, but however, there's one advantage. And the advantage here is actually you can be able to do localization using a single base station. Why is that? The reason is that for us, if you look at this figure, for example, these different antennas can be considered to be themselves as different base stations. And so using a single transmitter, I can actually do the localization. Spherical wave propagation is more accurate. You have to account for it. Otherwise, you have if you assume that you have a planar wave propagation, it's essentially equivalent to having channel estimation errors. As I said, it adds additional constraints that makes the localization better. So basically, you can do localization using a single base station, and because of that, actually, it helps in synchronization. So even if you don't have synchronization, spherical wave propagation, because the fact that you have essentially multiple base stations, the multiple antennas are essentially like multiple base stations, you basically are able to deal with synchronization. The last effect that I want to talk about is what's called a beam split. So the beam split is the following phenomenon. Because of the large bandwidth and because of the very tiny beam width that you have, the beam at different subcarriers, they point in different directions. Now, this is the problematic for communication because you will not be able to have the array gain that you want in a certain direction. The directions will be kind of like, varying. The allocations the directions will be varying over the multi-carrier. And this is affected again by various like effects, the bandwidth, the number of antennas, which affects the beam width, etc. So it's problematic for communication, but actually it turns out to be useful for communication, for localization, because you have more diversity in the directions you have, and so you are able to better localize your target. So kind of like just to kind of like end this talk, I've talked about we focus on terahertz, the terahertz spectrum. What we see is challenges that maybe kind of like we might have seen a glimpse of it in millimeter wave, but now it's kind of much more amplified. That amplification, in a way, could be at the outset like seen as a problematic, but in a way also it's enabling. It enables things like sensing. It makes like sensing and it makes localization and communication codependent. So what we expect to see as we use this spectrum to actually have more applications and a convergence of all these services. Thank you very much. Thank you, Dr. Zaidul. Thank you.
Is Dr. Zaidul here? Dr. Malik?
Okay. I didn't see the. Okay,
yeah,
so
there's no. I mean, the conclusion slide is this actually.
Okay.
So that's the conclusion slide.
There is one question in the Q&A. If you can address it, do you want me to read it?
Sure.
Okay, so thank you for this interesting talk. As you mentioned, terahertz signals suffer from extreme path loss, where even a sheet of paper can block a light of sight signal. Do you think it is realistic and economically feasible, given the extremely slow rollout of millimeter wave, to expect to deploy a huge number of transmitters, receivers for localization, and especially communication applications? Also for the application shown on the slide 23, sensing different gases, wouldn't it be cheaper and more reliable to use chemical sensors instead? This is a Ahmed Khan question.
Yeah, thank you very much, Ahmed, for a very interesting question. What I want to say is this. I mean, like, first of all, that's what I was alluding to. In terahertz, you are basically using much smaller wavelengths. And because you're using much smaller wavelengths, you can actually pack the same many more antennas in the same physical space. So the physical space itself will not change. The technology that realizes that many number of antennas will change. So what I was talking about is plasmonics. This is not my field, but plasmonics basically kind of like, which is based on graphene, promises to actually realize such a large number of transmitters and receivers. Now, when it comes to sensing, definitely, you can rely on chemical sensing, but I mean, this might be maybe useful in a factory and sometimes you want to have alternatives. The other thing I want to say is actually, okay, the purpose is not only just sensing, the purpose is also communication, because for you to be able to communicate properly between a transmitter and a receiver, you need to know how much molecular absorption you have. And to do that, you need to know what gases you expect to have in the room so you need to have actually sensing to enable communication, not for the sake of sensing itself. Maybe you can, so that happens by the device itself, and that's where terahertz allows you to do that. But thank you for a very, very interesting question.
Thank you very much. I will leave the other question for the panel discussion because of the shortage of time. And we will pass to welcome our last speaker for this forum. And after that, we will have the panel discussion and we can answer all your questions. So our last speaker is Professor Mohamed AlOuini. He was born in Tunisia. He received his PhD in electrical engineering from Caltech in '98, and he served as a faculty member at the University of Minnesota and Texas A&M University at Qatar before joining in 2009 King Abdullah University of Science and Technology. He is now a distinguished professor in the electrical and computer engineering. Professor AlOuini is a fellow of the IEEE and of the Optical Society of America. He is currently particularly interested in addressing the technical challenges associated with the uneven distribution, access, and use of information and communication technologies in the rural area, low density populations, low income, and or hard to reach areas. I will welcome with me Professor Salam AlOuini for his talk on connecting the 3 billion plus. The floor is yours, Professor AlOuini.
Thank you very much, Professor Zidouri, for this nice introduction, and thank you for our colleagues in KFUPM, first of all, for organizing this very nice workshop and for inviting us to contribute and share with you some of our recent kind of research development. So as Professor Zidouri mentioned, the title of my talk is Towards Connecting the Remaining 3+ billion. So let me share my screen. I hope you all see my screen, right?
Yes, we can see.
Okay, let me make it bigger. So I hope everyone can see clearly. So obviously, this is a nice follow-up on all what we have heard so far with the talk of Hesham and of Tareq and so on. So we know that 6G is coming, 5G is being deployed worldwide, and you know this 10-year cycle, which basically means that now we are, relatively speaking, early in the 2020 decade. So we are all planning for the deployment of 6G, which is planned to happen by the early 2030s. And obviously 6G will be like it was kind of covered in the previous talk about pushing the envelope, going to this higher data rate, going through this new application where there is conversion between localization, communication, imaging, and so on, and a few other kind of basically futuristic, I would say, application, some of them being displayed in the slide in front of you. However, I think we need to remember one key shortcoming of current generation of wireless communication system, including 5G, is that we still have about half of the world population, a number between 3.2 to 4 billion people who are either underconnected or not connected. And actually, the COVID-19 pandemic accentuated this and showed that essentially this connectivity divide is becoming the modern face of inequality between the have and have not in this digital context. Now, the reasons are many. I'm not going to emphasize in this talk, let's say, social type of reasons, such as, lack of literacy, like I'm saying, lack of computer literacy, people who don't know how to use phones or computers, sometimes lack of interesting or relevant digital content, difficulty of accessing the language. So all of this, of course, are also issues that are behind this digital divide. But let me focus on the technical, and it is linked to a certain extent to economical aspect of this problem. So first of all, one has to remember that to have reliable telecom network, you need to rely essentially on basically a power grid. And in many of these developing countries that are lacking connectivity, the main problem is that the power grid is either not there, or if it's there, is not reliable. So that's one issue that often we need to first solve. The second issue is like the economical model that the mobile network operator use, which is a model that basically rely on the so-called return on investment type of strategy, where you invest quite a bit upfront and then you get back your money by deploying your equipment in super dense areas where essentially through subscription you can recover your initial investment. So obviously that kind of thinking or that kind of strategy fails miserably when you have to lay hundreds if not thousands of kilometers of fiber optic to reach very sparsely populated low income, let's say rural areas. So this is the reason why we are having these bad type of statistics. Now, obviously, this is now becoming an important issue. Again, the COVID-19 situation made this problem even more important. So we really need to break this vicious cycle of digital divide and give these people who are at the base of the pyramid the opportunities that people are having in dense area or urban areas, so that they can access better health kind of system, better education system, get access to new job opportunities, get access to banking and financial transaction. All of this can happen as soon as connectivity is put in place. And in a way, actually, beyond just connecting the unconnected, if you are able to kind of create this global connectivity, we can move from this, let's say, or let's call it narrow smart city concept to something broader, including smart villages, smart hamlet, smart rural areas, in short, smart living, where people can be connected anywhere. And with that, people may choose not to live anymore in congested downtown areas that to be polluted and crowded and so on. So basically, people can choose to live in suburban or rural areas because they are well connected. And as we have seen in COVID-19 time, people can still work remotely very efficiently, especially if you have a very reliable high-speed connection. They can still commute once a week or so to have meetings, but remotely they can still access their job opportunities, good education, good health system, and so on. So that's the vision, or that's basically the objective of this kind of movement that many of us are pushing towards connecting the unconnected. So why is it a problem? I already mentioned that, but let me kind of describe it in a little bit more detail using this kind of graph or few graphs. So here what we are highlighting is the quality of experience in terms of high quality, high data rate and low latency as function of the cost per user in remote low population density areas. Obviously, classical low throughput geosatellite are very good for TV broadcasting, but they're not meant or have not been designed for internet browsing. And that such internet browsing through classical satellite system is quite expensive, or still quite expensive. Again, going through this point-to-point fiber optic or microwave wireless link is quite expensive. It is not scalable. It's not the way to go if you want to basically connect low density population areas. The holy grail of global connectivity is to be able to provide high quality of experience for basically people living in low population density areas at a low cost. So you need to have affordability as part of the equation. In order to fulfill this nice kind of vision that Tesla had 100 years ago, where basically he kind of essentially predicted 5G or 6G way ahead of its time. Now, how can we create this kind of global coverage? So obviously, it's very simple. You go against exactly what you do in an urban microcell environment where you try to densify. Go for these very small cells with millimeter wave or terahertz in order to get as many as user as possible per meter square. The idea here is rather to go for macrocell or super macrocell, such with a single kind of tower, you are able to cover as many users as possible in this kind of very large area that is sparsely populated. So one basic starting point is to reuse TV towers on the top of hills, on the top of mountains, capitalize on the VHF, UHF band. That's a very interesting band. It's in the low part of the spectrum, as you know. It's what you call front beach spectrum. It has very nice propagation characteristics, and it can give you this essentially tens of kilometers of coverage, and that can be one way to go. Sometimes you are not able to find the required frequencies, or you don't have the right kind of hilly type of environment to put your tower. So you can create an artificial tower in the air, and one way to do it is using the so-called tethered kind of platforms. So these can come in the form of balloons, airship, aerostat, blimps. There are different shapes and form, but the concept is the same. These are aerial platforms that fly at an altitude between 500 meters to 1,000 meters, 1 kilometer. They are tethered. The tether is there to provide power supply to the platform or to the payload. That can include, of course, an aerial base station, and also a backhaul, so a fiber optic that can backhaul the aerial base station to the ground, and in the ground you can have a satellite connection, or you can have a fiber optics. So this is a technology that is being kind of developed in few countries. In particular in the US, there are two big companies now, RTO Wireless and Alteros, that are pushing this concept of super tower in the air in order to cover rural America using this tower in the air. Now, if you want to go further, in the sense that with these kind of tethered balloons, the kind of coverage you get is roughly 30-40 kilometer radius coverage. You want to get a wider coverage for countries that are more sparsely populated, who do not even have a good kind of terrestrial infrastructure, like the case in the US. You want to go to higher altitude. And with that, you start hitting the so-called HAPS. So HAPS is an acronym for High Altitude Platform Station. Some people also call them High Altitude Pseudo-Satellite. So these are aerial platform. Again, they can come in different shape and forms, in the form of drones, in the form of balloon, or in the form of an airship, like an aerostat. They fly in the in the stratosphere. So the stratosphere is roughly at 20 kilometer altitude. So it's above the weather, above the atmosphere. And the idea there, they have more favorable wind conditions, and they can stay static pretty much like in a geostationary location. It's like, that's why it's called a pseudo-satellite. So there is no orbiting here. It's basically staying in a fixed position with respect to the ground. And the typical coverage area you can get with that is 100 to 150 kilometer radius coverage. So there are two pioneer projects, one led by Facebook a few years ago, Aquila, and another one more recent by Loon in Google. Both were technically successful. Unfortunately, they were not able to go to the business or commercialization phase at a large scale, and as such, they have been stopped. But the good news is there are many other startups worldwide, in the UK, in the US, in Japan, that are trying different kind of HAPS, and many of us in the community believe that HAPS will be part of our ecosystem by the early 2030s. One main characteristics of HAPS is that it's basically an airplane or a drone, if you will, that can act as a backhaul and access solution at the same time. So in other words, it's an aerial base station, and the user on the ground using a standard phone, a standard smartphone, iPhone, Samsung, whatever you want, can connect directly to a HAPS. You cannot connect directly with your phone to any LEO satellite. Okay, I mean, there are some very minor experiments of people texting to a LEO CubeSat, but in general, a 4G or eventually a 5G connection cannot be established with current technology with our standard phone. The budgeting doesn't allow that. However, with the HAPS, you can just have a standard base station in the HAPS, and you can use your standard phone to connect directly to HAPS. So that's one of the major advantages of a HAPS compared to any satellite solution. And the HAPS can be, of course, backhaul to a gateway on the ground that can link the end user to the internet. So eventually, Of course, you want to go for even bigger coverage, and for backhaul solution, you need to rely, like we have done for many, many decades now, satellite communication. So satellite communication, as you know, are very popular to connect the unconnected, but they are also popular for maritime communication and aeronautical communication, which is another form of connect the unconnected, where you're in the middle of the sea or in the middle of the air, where there is no other way to connect the people or devices or IoT sensors that are scattered in the ocean or in the air. So satellite communication is another area that is booming in view of this demand for global connectivity. And when we talk about satellite communication, we talk about different families of satellite systems. So obviously, we are all familiar with the classical geostationary satellites, but there is a big evolution in that particular technology. There is kind of a direction towards making them smaller geosatellite, more with higher performance, and basically with much higher throughput. And actually, I chose in this talk, it's just a half an hour talk, to particularly focus on this next generation very high throughput satellite. So I will spend quite a bit of time talking about that as we progress in this talk. But there are, of course, if you want to lower the latency, you may want to go to lower orbits, so medium Earth orbits such as O3b or SES, or even lower orbit. And here we are talking all the way to this very basic CubeSat for sensing at 160 kilometers, to this mega constellation that probably you all heard about, led by the big tech companies like SpaceX Starlink or Amazon Kuiper or Telesat Lightspeed, Inmarsat Orchestra. There are probably 10 projects ongoing, and the Chinese also project is a huge one. All of them are after these 100, if not thousands of satellites being launched in the coming years and creating this umbrella to provide LEO coverage. And with LEO coverage, we are talking about satellites that are not geostationary, so you need an orbit, and they are going around. And as you heard probably recently in Saudi Arabia, there was also kind of an agreement between NEOM and between OneWeb, which is one of the projects, to basically have LEO coverage on the country. So it's something that's going to happen. It's just a question of time. We are going to see many of these constellations maybe coexisting, or maybe there'll be some winners and some losers, but that's something that is moving at a very high speed. Now, nonetheless, I chose today to focus on another kind of aspect of satellite communication, which is what I call, not me, myself, what we call, I would say, hybrid, very high throughput, geostationary satellite with site diversity. That's, in a way, you can view it as a competing technology or as a companion technology to LEO satellite. So this is kind of natural evolution of geostationary systems. So what we are talking about here is geostationary satellites, but they are very high throughput. When I say very high throughput, we are talking about satellites that can handle at any given time around 1 terabit per second. That's a huge amount of information that this kind of satellite can perform. These satellites have two sides. One side is called the user link side, which is basically these beams that can be steered to different directions, that can be adjusted according to traffic demand between day and night, between land, between sea. So this is kind of things that you can move around depending on your traffic conditions. And every beam can be basically offering, like, let's say 1 or 2 gigabit per second. And if you have hundreds of them, or like thousands of them, I think you can have like hundreds of them, aggregate together, they can reach to this 1 terabit per second that can be processed. Obviously, satellite is acting as relay, so the whole thing has to be backhauled. And currently, with so-called high throughput, not very high throughput satellite that, for example, Viasat is using, they're using Ka band. Ka band is a band that is becoming scarce, or at least is envisioned that's going to become scarce by the 2030s, because there is heavy competition with IMT or mobile communication. Ka band also maybe start being used in the basically for the user link. As such, the project or the goal is to start using optical feeder links, meaning by that free space optics. And actually, that's what attracted this project initially, because I've seen some paper having been active in the area of FSO over the last 10 years or so. I have seen people working more and more on how to use FSO to connect satellite to the ground. And here comes two major problems. One problem that is very well known in the FSO community, which is the pointing acquisition tracking, the PAT. How can you make sure that the FSO beam remains completely aligned with the satellite that is at 36,000 kilometers away? That's a big challenge. People have done it in DLR in Germany, in basically NICT in Japan, And this is some of the work we are trying to do here at KAUST also. Now, the second problem is something that really is very, of course, problematic for these satellites is weather, atmosphere. You go through the weather, you may have clouds, you may have fog, and that's the big enemy of FSO. So obviously, if you have a cloud on the way, the only solution is to kind of go to another site, and that's why it's called site diversity. So typically, when we deploy this kind of hybrid, and by hybrid it means that one side is RF, the other side is optical. By very high throughput, we mean like 1 terabit per second. And by site diversity, we are saying that if you get blocked somewhere, you need to have a network of optical gateway station. Like for example, in Europe, they're predicting or planning to have 9 or 10 of these strategically located optical gateway stations to make sure that if you're blocked in London, you can get your signal from Mallorca or Lisbon, something like that. So that's a concept of these very high throughput satellite. So within that, what are the kind of research we are doing? Let me take a couple of maybe papers that I can highlight. So one paper is led by Dr. Salman Bashir, who's a senior postdoc in my group, and who's really, I would say, one of really world expert in this, because he has done his PhD in Purdue on this topic, and he has continued doing his postdoc just working on this path problem for FSO. And the main idea that he's advocating for is basically using an array of detector in order to relax the basically pointing, acquisition, tracking on these FSO beams. Now, what does it mean? The concept is very simple. So here is basically an FSO link beam that's in red with different contour of intensity, and then your detector is in magenta. Obviously, if you are misaligned, you are going to lose quite a bit of the intensity. The idea, instead of using a single detector, is to rather use an array of detectors so that you capture a maximum number of the intensity. Nonetheless, even with this array of detector, you need to kind of think of how to design that in an optimal way. So in terms of acquisition, in terms of tracking, and so on. So let me show you an example of a design that needs to be basically taken care of. One problem is acquisition time. So typically what you have a satellite, you roughly have information where the satellite is. That's known as the uncertainty region. That's the blue region. You roughly know it's usually 3 times the standard deviation of the vibration satellite. So you assume Gaussian vibration of the satellite around a certain point, and your 3 times the standard deviation will give you the so-called uncertainty region of the satellite location, which is the blue region here. But then you have to lock exactly on where the telescope or where the detector is. And to do that, there are many ways to go through this uncertainty region. Some paper by Joe Kahn, like a very famous professor in Stanford, a few years ago, came up with many kind of, let's say, experimental way of scanning this uncertainty region. And they showed experimentally that going through a spiral is actually the best way to do. And actually, indeed, we tried different approach, like what we call the shotgun approach, a square approach, and spiral approach seems to be the best approach. And now, how quantify the acquisition time, or like the statistical acquisition time? So basically, you go through the spiral until you lock on the signal, right? So the acquisition time is going to be TS. TS is the scan time. That's the time it takes to go through full scan. Why do you need sometimes to go to full scan? Because it can happen that you go through a full scan, and although you passed by the detector, obviously sometimes you have a misdetection, and you kind of go around it without feeling that it was there, and that means you have a misdetection, and you have to go through a full scan and then repeat again. So TS is the scan time. X is the number of failed attempts, which is a geometric random variable, plus TD, that's a dwell time. That's the time you take to shine the beam at one particular location, then move to the next location as you move slowly through the spiral. And W is a fraction of time in last successful attempt. In a nutshell, W is going to be kind of function of this vibration, the X and Y dimensions are Gaussian, but because you look at the magnitude of that, so it's kind of, and the magnitude is really in the power with W is proportional to the square, it's exponential. To make a long story short, what TU is a random variable that is the sum of a discrete geometric random variable and an exponential random variable that are independent. And luckily, what Salman was able to do through a very simple convolution, he was able to get the statistics of the acquisition time in closed form, including the complementary CDF. Why is interesting to have that kind of statistics? That give you basically the violation time. So basically, let's assume you have a deadline. You need to lock for basically gamma, which is a certain deadline above which basically you declare an outage because you can exceed the deadline. That's now obtained in closed form as function of the system parameter, which are the beam radius and the number of basically the number of detectors and the scan time and so on. So let's see like what kind of results we get. So obviously this statistics, this kind of violation time goes down as basically you start involving more detector, which is what we'd expect. The more detector you have, the better results you get. But then the other interesting kind of design parameter we were able to optimize is the so-called beam radius. As you can intuitively imagine, if you make the beam radius very small, this red spot very, very tiny, then it will take you forever to do a scan. But then you have a very nice detection. So basically you don't have a high misdetection, which means it takes you a long time to go through the whole scan, but basically pretty much you'll not miss the detector once you hit it. Now, on the other hand, if you make this beam the red kind of spot here very big, then the scan can be done very quickly, but then you lose in terms of what happens is that the beam becomes less sensitive, let's say, or detector becomes less sensitive because the radius becomes bigger, and you can have a more often misdetection, which means you may have to go through different rounds of going through the spiral. That's a trade-off, and that has been reflected in this curve. So you see here, this violation probability has a minimum, and this minimum is like the nice sweet spot where basically you need to have the optimum beam radius. It should not be too small, it should not be too big. And that's kind of a system parameter we're able to optimize based on this analytical framework. So that's give you a flavor of some of the research we can do in terms of pointing, acquisition, tracking for these FSO links over long haul ground to satellite systems. But of course, satellite, as I told you, have a backhaul aspect, but it has a link aspect or the user link aspect. And with that, actually, we are using several technologies. By that, I mean, we are moving from just kind of this kind of broadcast type of situation. This is already in place for the current satellite. We are just trying to kind of push the envelope and be even more spectrally efficient the way we did it in terrestrial network, which means you want to more aggressively use the spectrum and reuse the spectrum in a more aggressive way. So this is a paper that was led by Dong-Yoon Na, as one of our PhD students, and mentored by Ki-Hong Park and under the co-supervision of Professor Yong Chai Ko in Korea University and myself. And the idea here is we use the stochastic geometry-based approach in this context to be able to assess the level of interference that is created in regular deployment of these multi-cell satellite-based systems. So this has not been done before, and that was our contribution in this paper that is going to appear very soon. So, you know, in contrast to single beam that basically have like this kind of global coverage, we are going to go for this multi-beam where you have frequency reuse. So here, for example, if you see a red and a red, it means that we are reusing the spectrum, but of course this comes at the expense of creating some co-channel interference, exactly the same way we have it when we use the concept of frequency reuse for cellular terrestrial network. But with that, by reusing the spectrum, we can become more spectrally efficient, and we can basically accommodate a higher capacity of user overall. Now, the kind of system parameter we had to take into account is the beam pattern of the satellite, kind of beam towards the ground or to the users. And then this is a very well-known fading model that we developed 20 years ago when I was still in Minnesota. It's called the shadow Drachen, but because shadow Drachen is kind of a very complicated channel involving a log normal Drachen, it's not a closed form. What we did in a very early paper, we changed Drachen by a gamma, and so we did some manipulation by kind of converting some of the log normal to a gamma and some of the Drachen to a gamma, and manipulating all this, we ended up with a kind of a modified gamma-gamma channel that led to this quite actually popular so-called shadow Drachen, but it's not anymore log normal Drachen, it's just based on a gamma type of model, Nakagami type of models that has this closed form expression. So this was our kind of system and channel model, and with that we tried to compare, assuming this kind of point process distribution of user on the ground, the performance of a single beam versus multi-beam. Now, just to remain within the time allocated to me, so we were able to look at for a single beam, try to find basically the CDF SNR and then the CDF of SINR. So for this is the CDF of SNR for single beam of SINR. When we start talking about multi-beam, I mean, in a single beam, we were able to get some kind of analytically closed form in the form of two integrals. For the multi-beam, it's very complicated, multiple integrals, but we were able to get the closed form expression on the asymptotic regimes. So let me just go to I think this is what makes, just to remain on time, what make more, made the method, let's convey the message. This is a trade-off that we want to quantify. So obviously, the more aggressively you use the spectrum, like for example, if you reuse of 3, that's of course a very spectrally efficient deployment, but then the price you cost, that costs you, you have a strong ouch probability, right? Now, on the other hand, if you go for a reuse of 7, then obviously you are more relaxed, you are less spectrally efficient, but you are more relaxed on spectral utilization, but you are able to quantify exactly how much you gain in terms of beta rate or in terms of ouch probability. So that's a trade-off. You can go for single beam, get very good performance, but you lose in spectral efficiency. You want to increase your capacity, increase your spectral efficiency, you use spectral reuse like we do in spectral in cellular networks, but now in satellite context we are doing that, and you gain you gain in basically spectral efficiency, and you lose in terms of performance, but maybe still acceptable depending on the type of quality of service that you are asking to do. So this has been summarized in this table where we are saying a single beam gives you low ouch probability, low symbol rate, but a low spectral efficiency. And in contrast, when you go with the multi-beam, very high throughput kind of paradigm, you kind of, we have to live with a higher ouch probability and a higher symbol rate, but you will gain in terms of spectral efficiency. Now, one last couple of slides, 2 exactly slides, to kind of convey that research in connected and unconnected is very much connected to another type of research. This is research that is in the area of depending on the community, on demand, or pop-up network, or some people call it network in the box. By network in the box, what we mean is you have a situation where you have connectivity and suddenly you lose connectivity. For example, a natural disaster. So you need to deploy a network on demand by bringing boxes, and basically they have the autonomous and they can basically start operating right away. You have basically an event with a lot of kind of user coming at the peak time, or a soccer game or a concert, and basically you need again some offloading that has to come from some basically you know, as simple as cow, like cell on the wing, on the wheels, but like that's kind of can be viewed as kind of bringing extra connectivity in this case to something that is saturated. You send some basically scientists in the middle of nowhere and you want to stream their video in real time. That's again connect the unconnect because there is no connectivity there. So you need to put in place a network in the box that can connect to a satellite or to a hubs and eventually connect this user to the network. So we started like a few years ago working on connect the unconnected, but automatically we found ourselves solving problem in disaster communication and in network in the box for maritime communication and for basically connecting people in unusual or hard to reach environments. And this is my last slide, which is also this interesting connection between future communication system and future transportation systems. As you know, again, because of the congestion in some of the big cities, there is a big kind of movement towards going for this aerial solution. By here, I'm talking about using drones for transporting merchandise, using drones or let's say flying cars or flying taxi to move people around within a city. These kind of flying vehicles at an altitude between 200 to 500 meters will need some communication capabilities. First of all, because they need to communicate among themselves and with the network to make sure they are navigating in a safe way. But of course, if you are talking about people flying within the flying taxis or basically merchandise that may have some IoT device connect for them to be able to be tracked, we need to be able to communicate with the people and device within these transport, with these basic flying vehicles. So, and with that, I believe that the HAPS paradigm or satellite communication paradigm can help basically essentially these flying vehicles. And actually one of the work we are doing now is trying to look at the trade-off. I mean, how should we kind of use the terrestrial network by using tilted antenna towards the sky and maybe create some interference to the cellular network on the ground, or rely rather on aerial network to basically basically serve these flying vehicles. So that opens up all these interesting problems that hopefully can lead us to some interesting new research topic over the coming few years. So with that, I would like to thank you for your attention. Again, I would like to thank all the group members and collaborators that contribute to these different projects. And we are all here towards hopefully achieve this, again, this interesting kind of visions that have been put forward by Tesla about a century ago. When you read some of his writing and text, I mean, it's amazing how visionary was Tesla at his time. Thank you for your for listening, and I'll be happy to take some questions, or we can move to the panel.
Thank you very much, Professor Slim. I think we have the last session in this forum, the panel discussion. So I will pass the floor to Dr. Alim Gable to moderate this session. But if you want, I can start with some questions that are maybe given for Dr. Salam AlOuini just now. If you or you can take over, and I have recorded the other questions. Dr. Ali, can you take over?
Okay, Bismillah ar-Rahman ar-Rahim. Can you hear me very well?
Yeah.
Yes, yes.
Okay, so I'd like to thank you very much. I'd like to thank the speakers. First, Professor Salim, Professor Salam, Professor Tareq AlNaffouri, Professor Moinuddin, and Dr. Hesham for the very interesting talks. I would like also to thank Dr. Abdul Malik and the department for their excellent arrangement. I'd like to thank KICS, Dr. Mohamed Moinuddin, for accommodating the changes, and would like to thank Dr. Hesham and Dr. Anas for working on the organization from the IRC side. As you know that this forum is arranged by different entities. We have the E department, we have our newly established center, and I will take 1 minute to explain about our center. We have the IRC, Interdisciplinary Research Center for Communication Systems and Sensing. And I think it is a very good opportunity that we have now a very well dedicated, focused center for communication and sensing. Maybe the first point, which is worth discussion to bring to the table, is this convergence that is happening between communication and sensing. So with going from 5G to 6G, there are lots of changes. So maybe one of the questions, maybe we can hear the input from the respected speakers about how do they envision the convergence between communication, radar, and sensing, and other technologies. While you prepare your answer to this question, I will just double check. By the way, we have chat and we have Q&A. So if you have questions, please use the Q&A for writing your questions. So looking for questions from the audience first. And I pose one question related to the relation between sensing and communication. So there are some questions, I give the floor to all, related to, some people are afraid about hazard-related health issues with 5G and 6G. So anybody would like to take this question, take this point?
Yeah, I can mention that if you want. So is the question in the chat, or is the question in the chat?
The question was in the chat.
In the chat.
Mr. Muhammad,
okay, sorry, let me open the chat. Anyway,
I can read it for you, Dr. Muhammad.
My question is how?
Okay.
There are many questions. I'm trying to find which one it is.
Maybe I will come to them. For example, this guy saying, we know that more number of transmitters around us, the more we will be exposed to higher frequencies, and higher exposure to higher frequencies will lead to a health issue. What range of tetrahertz frequencies are safe for health exposure?
Okay, let me, okay, I can give my answer. Maybe if you want, I can start, or maybe anyone else want to start? I can start if you want, but.
You can start, Professor.
Okay, so basically, I think we have to kind of clarify issues here. So when you talk about spectrum, there is what we call the non-ionized and the ionized part of the spectrum. So when we say ionized part of the spectrum, we are talking about X-rays, UV rays, gamma rays. These are, of course, very dangerous type of radiations that we have to be super careful about, and obviously we are not using them to basically communicate, at least so far. Now, why? Because they are ionized, which means they break atoms, they can affect our DNA and so on. we are still operating even in the millimeter wave, even in the terahertz, even in the optical band, in the so-called non-ionized band, which means as long as we are within the threshold that have been established by the World Health Organization and ITU, and that are basically applied in a with different level of, let's say, rigor, I would say, in different countries, obviously we are way below the thresholds. I mean, let's assume, I don't know the numbers, but we wrote a survey like 1 year ago, and if the threshold is 10, typically everyone's going to 1, to basically as a regulation, to tell you how conservative are typically the countries in their regulations and worldwide. Okay, so we are still in a very safe regime. This is from a heating perspective. So when you say ionized, non-ionized, basically the amount of heating you can get from radiation. Now, some recent, actually, we have a grant on this topic, and some recent measurement done by some of our collaborators in Italy are showing actually that with 5G, because it's like a shorter range, because it's lower power, actually 5G is even less, I would say, they are getting less radiation from 5G than, for example, 4G, if you want to make comparisons. So really, there is nothing to worry about from like a SAR perspective, you know, like this is a measure that is used to kind of measure the level of exposure. And one thing that I think sometimes is confusing to people is that people think that most of the radiation is coming from the base station, which is not true. Actually, a lot of measurements are kind of showing that most of the radiation we're exposed to is actually coming from our own phones, from our own tablet. We are most of the time very far from these base stations. When I say very far, even like tens of or hundreds of meters. By the time the signal arrives to us is very weak. But the signal that can affect us is the signal coming from our own cell phone or from our own tablet, especially when we are using it in an uplink mode in an area at the fringe of the cell, where basically the phone is operated at full power. This is when you get most of your exposure. So if you want to minimize EMF exposure, you need to come up with techniques or with approach to minimize the amount of power coming out of your phone, which means to kind of, we are proposing some approach like decoupling and so on. But that's one approach. So what I'm trying to say, and to summarize and wrap it up, there are two ways to tackle this problem. Number one, I think there should be some extra effort from our colleagues in biology and medical schools to try to quantify better the effect of millimeter wave, terahertz, and optical on our body, on our health, beyond the thermal effect, beyond this paradigm of ionized, non-ionized. Maybe there are some other biological effects that are triggered by this kind of radiation. That's something maybe still open, or people have to dig a little bit more from biomedical perspective. So that's one track. The second track, which is our track as engineers, I think we need to make more efforts in designing what we are calling EMF aware, electromagnetic field radiation aware network, which in a nutshell means we want to develop or design networks that can perform up to expectation, given a certain quality of service, but with minimal EMF radiation, using, for example, decoupling, uplink, downlink, using IRS, etc., etc. So this is an active research area, and people are aware that future systems have to be more and more basically careful about EMF radiation. Sorry, it was a long answer, but you know, I know it's often a problem that people are aware, are worried about, you know.
Yeah, I think a very excellent and detailed answer. Thank you, Dr. I really have my answer, but I thought since it was asked from our respected audience, so I forwarded the question to the panelists. So there's another question, if you allow me, to Dr. Tareq, Professor Tareq, regarding in practice. He's saying, can we use terahertz in direction variable estimation? Antenna arrays. If you want, do you want to continue the question? Just
no, please go ahead. Please go ahead.
So he's saying, just to explain the question, he's saying, in terahertz, lambda would be very small, and then using arrays, whether uniform or sparse, will have a spacing between elements, which is comparable to the size of the antenna. So I think the question will be clear to you, Dr.
Right. So, okay. So, I mean, that's an interesting question. Usually people talk about, I didn't think of, like, you know, the use of sparse arrays in a terahertz scenario. So the question by itself is interesting. However, what we can talk about is actually sparse subarrays of antennas. So basically, in that, for example, let's assume for the sake of localization, you might actually, by using sparse arrays, by using different configuration of sparse arrays, what you might end up be able to do is to kind of like, localize users in different directions, or you utilize multiple users. If you use the full subarray, you have an array gain, and so you can kind of like, target a certain user at a certain direction for communication purposes, say. But if you use sparse subarrays, what you can do is you might be able to, you will reduce the array gain in one direction. You will have multiple peaks. So you might be able to actually localize and communicate with multiple users. Now, regarding the issue of ambiguity that happens from sparse arrays, the issue related to the wavelength separation between antennas, what I want to say is this: if what you have is non-uniform, if the arrays you have are non-uniform, then the ambiguities that you have are resolvable. This is well known. So if you have like subarrays that are sparse and they are non-uniformly placed, then you can resolve any ambiguity. Last point, within the subarray itself, it doesn't make sense to have a sparse array. It makes sense to actually to make use of all of the antennas within the subarray. The sparsity we can talk about within the subarrays themselves. I hope this answers the question.
Thank you, Professor Tareq. We have other questions in the chat. So we have some questions from, I think, Dr. Muhammad Zaid Khan. Some of them are related to the health issue that he was suggesting the use of EMI filters. And there is another question related again to how can we overcome radiation hazard after optical fiber communication for 6G? Anybody wants to comment on this? Okay.
I just want to maybe I make one comment. It's kind of like in line with what Dr. Steen mentioned, which is basically like say in terahertz, in a terahertz context, because the communication has to be, the beam widths are like very narrow. They have to be kind of you have to have alignment, you have to have directivity. You cannot deal with omnidirectional antennas that you are, for example, using in 4G, say. All of this makes sure that with a properly designed communication system, actually the radiation is going where it's needed. This is of course on top of the fact that Professor Slim mentioned, which is basically like we are way below the ionizing energy that we're dealing with. And so the convergence of localization and communication actually might be helpful in that direction, because you're localizing the receiver before actually communicating.
Okay, so another question, again, it's a strategic question related to the future from Mr. Hadi Barak. What do you think we will see in the future? More deployment in 6G or satellite coverage? So if you would like to comment on this, any of the panelists would like to hear all of you also. Dr. Salam, are you here, or Dr. Hesham, Dr. Moinuddin?
I can, if you allow me, I can shed some light here.
Yes, please, Dr. Salam.
Is my voice clear?
Yes, clear.
Right. I think I will take it from the what Professor Slim started to talk about the rural coverage. Satellite communication and in general the LEO and the HABs and the others will be mostly or mainly used to provide the connection or connection to unconnected, as he mentioned, as well as it may be used mainly for the backhaul communication or providing backhaul in places where laying optical fiber and so on is extremely prohibitive, either expensive or mountainous and other places where you cannot lay optical fiber. So satellite and in general the space communication, whether UAV and whether the satellite high altitude or low altitude, I think their focus would be mainly on these type of applications, either to connect the unconnected or to connect the lower altitude terminals like the hubs and others instead of laying down optical fiber. While the 6G, 6G will be an umbrella where basically all these will be involved. However, the other communication types that 6G will also allow for, like the massive type communication and the combination of the different services that 5G provides, will be mainly for places where satellite cannot serve. Like, for example, the using terahertz communication for the sensing, imaging, localization. All these cannot be even, you cannot even provide it using satellite because of the distance and because of the different application that the satellite can provide. So I hope this kind of provides
Thank you,
a good
Professor.
answer. Thank you.
Thank you very much. There's one more question in the chat.
Can I add one point?
Yes,
here,
sure.
if you don't mind. I just to confirm what Dr. Salam mentioned. I think this is just like to give maybe a perspective that maybe is important to mention. Some of you may remember in the late 90s, early 2000s, there was also this big movement behind satellite communication. You remember maybe Teledesic or Iridium. Iridium pretty much survived, Teledesic collapsed. And the reason, in my view, is at that time, we had like cellular technology and satellite technology, or these two kind of networks were kind of evolving on two parallel paths. They were not trying to work in a collaborative path. Now the things have changed, and the buzzword of today is so-called integrated space air ground, or integrated satellite drones like terrestrial base station, which means, as Dr. Salam mentioned, 6G will be actually this kind of architecture where you will see this mix of different type of network. For the end user, at the end of the day, he will be always talking, or should be talking to kind of basically either an aerial base station or to a terrestrial base station. Now, how the backhaul is done? Is it done through a fiber optic, through a satellite, through HAPS? That's not the business of the end user who will be using the same phone. There will be no, just to make it very simple, as you may remember, the early days of the satellite communication system like Thuraya and Iridium, they have special phones. So you need to buy a special satellite phone to be able to communicate. The vision or the future of these integrated networks is that the same phone that you use in an urban environment is the phone you'll be using during your maritime communication or while being in the desert. And the network will take care of backhauling you according to the available resources. So that's the key words, that there will be an integration between these networks, and 6G is going to be, hopefully, or beyond 5G, will be kind of this manifestation, or this kind of, hopefully, I would say, they will deliver, 6G will deliver on this integration between these different networks.
Thank you. Thank you. Another question in the chat saying, after thanking the speakers, saying, my question is, do we see HAPS or high altitude platforms as RIS, as reconfigurable surfaces as well? So my question is, do we see HAPS as RIS as well?
Yeah.
So
I mean, should I answer this question, or?
Yes, it's okay. I will leave the floor after you, Doctor. If somebody wants to add after Dr. Salim, he's welcome. So go ahead, Dr. Salim.
I mean, I just have a quick answer. Is like, yes, people have been proposing to use HAPS because HAPS is relay. So basically, you can cover the HAPS with an intelligent reflecting surface and use them as a reflective relay. And there are very many papers now on using drones and using HAPS as a reflectors. So Dr. Halim, for example, in Carleton University in Canada, has been very active in the HAPS area, and in particular, he has a couple of papers on a combination of HAPS with IRS.
Okay, anybody wants to add to this question? Okay, so I think there's one other question. I think maybe you have touched on the answer. He's asking about the effect of fading effects of terahertz line of sight, with especially in the presence of high-rise buildings or structures. So what about the fading effects of terahertz and loss with end user in high-rise buildings structures? I think yeah. Go ahead,
yeah. So as I said, like, you know, the terahertz, as I mentioned in my talk, suffers from various blockage issues, like, you know, path loss, number one, molecular absorption, blockage from, like, you know, the structures, the humans themselves, the transceivers themselves, and so basically, like, you know, you have to deal with it. So one solution is the use of a massive number of antennas to kind of, like, you know, beamform, have array gain, and, like, you know, to your target. The other solution is you have to deploy your access points at an elevated height to avoid these obstacles. The third solution is to actually have multiple access points. And finally, you have to have hybrid solutions, which is basically like, RF and terahertz, so that like, you have like the best of both worlds: coverage that's kind of guaranteed by RF, and rate that's kind of guaranteed by terahertz.
Thank you very much. There is another question posed to Professor Salam, saying one of the problems with DRL methods is that the neural networks are designed with the fixed input-output sizes. So if the number of antennas or users change, we have to retrain from scratch. What are your thoughts on overcoming this? Is the question clear, Professor Salam?
Yeah. The nice thing, the good thing about the deep learning, deep reinforcement learning, is that it's basically a general approach to learn the environment as it goes, basically. So one part of the answer of this is, if you basically have a solution for a specific network, and then a user started, some users left and some other users joined, which will basically change your network structure, the number of antennas or the virtual number of antennas, if the number of base stations is the number of antennas in this case. Then in this case, you can use the solution that you reached at the previous network as an initial point, and then start again reinforcement learning to come to learn as you go the new solution or the new optimal solution. Of course, training, as you mentioned, takes time. However, as you go, you will continue to adapt your network until you reach a specific point or an optimal point that the reinforcement learning will give you. So it's that's one of the advantages of the reinforcement learning. It learns as it goes. So even if things change, you can still continue without starting from scratch. I hope this answered the question.
Thank you very much. Now let me put one question to you all, and then maybe I'm looking for a short answer. As a user, I'm not feeling I need to switch from 4G to 5G, although it might be already there, sets already there. Are we getting into saturation? Is the importance of the generations reducing? So what is your thoughts? So we can start, Professor Salim.
Yeah, I mean, I'm not sure. Maybe the incremental. I mean, if you are after just extra, I would say, if you're happy with the kind of speed you're having now, then maybe yes, maybe you don't need to go from 4G to 5G. Yeah. If you are going,
I mean, I don't like before the video speed and so on. We feel the pressure to move to the next generation, but now it's almost instantaneous.
Yeah, what I'm trying to be after is. What I'm trying to convey is, if you are happy with the kind of speed you are having now because the kind of application we are using are being delivered with a high quality, maybe there is no incentive for you to move to 5G or 6G. But if your kids are going to be more attracted to this virtual reality, augmented reality type of environment, then these are very greedy type of application that will may need the terabit per second that Dr. Tareq was talking about. Okay, and then if you are one of this nomad that is traveling every week somewhere, and you want your phone to be roaming and working where you are in the airplane, in the train, in another country, you may want to have these international phones that can connect anywhere to anything, and that's like going to this connect and connect, or this global connectivity kind of concept that is still not there. As we know now, it's quite complicated to roam or to have connectivity. It can be quite expensive and not affordable. So there is always room to improve, and there is always room to find the incentive for people. But sometimes these kind of, I would say, things happen gradually, and the generation maybe take advantage. We're getting old, maybe you and me, Dr. Ali, but there are people who may be more interested by this.
So we are which G? Are we 3G or 2G or 5G?
Yeah.
Okay, so there are human generations and there is also mobile generations. So, Dr. Hesham, do you want to comment on this or on the issue of convergence between radar sensing and communication?
Yeah, sure. As Dr. Salim said, it depends on the application. Sometimes applications we don't need much more. If you are web browsing or you're using some, like communication, regular communication. But for example, 4G does not give you the ability to have this integrated physical and like physical and data or cyber world. So if you need like automated vehicle, autonomous vehicles, connected vehicles, UAVs that do the delivery of packages and this kind of application, then you have to move to 5G. Because like 4G we cannot do that. And if you want to go to beyond that and you want to integrate the virtual, physical and digital world, then you have to go to 6G. So it's driven by the application, what you need. So some application actually 4G and below fall short to satisfy. You cannot just use them there.
Okay, thank you very much, Mr. Hesham. I think the pressure will not come from the individuals, but like you said, from maybe institutions, governments, and so on, because of the different applications that are there.
But if I may add also, Dr. I think we are from a different generation. I mean, we live in our, our bubble, etc. I'll give you one example, just one example. This is something that happened, rare that happens, but I went to the Spanish Super Cup that happened in Jeddah here. And connection was impossible. So, in our regular life, we don't feel the need to go to a new generation or a new technology, but this is kind of like a telling example. And the new generations who are less technology averse as compared to us, who will definitely welcome, such an upgrade.
Great, thank you. I think
I have one comment, if you allow me, Dr. Ali.
Yeah, okay.
Yeah, I think this is a very interesting question. To answer it, let's go back to the early 2000s, where basically 3G was about to be implemented. And at that time, we used to have the Nokias and the Motorola's and so on without the smartphone. At that time, everybody was questioning, why do we need an internet over the phone? Basically, there's nothing to do there's nothing much to do over the phone to explore internet and so on. So basically, as hardware started to enhance smartphones, improved and so on, 3G became obsolete and 4G was fully utilized. And now we are talking about 5G. So as equipment enhanced, as application pop up and become the mainstream, for example, for us, probably our generation probably may not buy in the virtual reality or others. However, the younger generation, basically they are born in this. So they will find it weird after 10 years not to see things evolve in a natural way, where basically games are not anymore played as on the screen. They are basically played in a virtual reality screen, and so on and so forth. But adding to that, the new trends like the autonomous cars. This is a very strong trend that is coming, and when it comes, our life will be different. So we'll talk about autonomous cars, we'll talk about flying cars, and so many other advances that our cities will never exist as we know them now. And this basically will push the 5G, the 6G, and probably the 7G after that to allow for these such advances. Thank you.
Thank you, Dr. I'd like to listen to Dr. Moin just to give a fair chance to everybody. If you want to add something.
No, thanks. I think so already Professor Salim and Professor mentioned. I don't think I have to add anything.
I'll make you defend 6G strongly. So I agree with you. And we're talking with the kids regarding even buying a display. They speak about response time being less than 1 millisecond. Otherwise, I don't want this display on. Speaking of gamings and real-time response and so on. So any comment regarding the integration between communication, radar, and sensing? Okay, so if there are no more comments, I just give one last one.
Ali, there is some questions. For example, Sayyid Sadaqat is asking, is there any difference in beamforming between 5G and 6G? Was this question addressed?
Okay, I think that the entire presentation was about the difference between 6G and 5G, about the frequency. And do you want to add that who was presenting this?
Yeah, I was presenting about beamforming. So I mentioned that the issue of spectral efficiency, and we do not have channel reciprocity available in millimeter wave and terahertz. We have to go for statistical beamforming. Also in 6G, people are talking about pencil beamforming. As Dr. Tareq mentioned that the beams are very narrow, and in that case, the beamforming task is very challenging. It's a very narrow beam. The angle will be very precise for the desired user. So the beamforming task will be more challenging, and we need to have more precise solution to address this problem.
Thank you very much. I think we're getting close to the end of the session. So,
Dr. Ali, there is one more question in the chat.
Yeah, I have read some of the questions, but some of them are,
okay.
I think.
From Fawaz?
Which one? From Fawaz? The Q&A or from?
No, in the chat. Would we need access points, relays inside homes, since the terahertz suffer from penetrating hard structure walls?
Yeah, I mentioned that. I mean, like, you know, the coexistence between RF and terahertz is the solution for this. Now, another way of talking about relays is reflecting surfaces. So if you think about it, reflecting surfaces are actually acting as an instantaneous relay. It's kind of like providing more, like, you know, if you want non-RF tight paths for the channel in an intelligent way. So these two solutions, hybrid solutions that can penetrate the blockages or reflective surfaces, are two ways of dealing with that.
I think the other questions I already have seen them, so maybe they were addressed somehow, or they require longer time. So because some of audience are starting to leave for the prayer, I would just like to go over if you have anything to say before we conclude the session. Last word, something you wish you have said, or we can conclude the session. Okay, anything? So thank you very much.
If anyone would like to ask a question or also live from the audience, we can give him the floor to speak if you don't want to write down. One or two questions before the wrapping up.
I think we're good, Dr. Malik.
Okay.
So thank you very much, everybody. Thank you, Professor Salim, Professor Tareq, Professor Salam, Professor Moinuddin, Dr. Hesham, for your presentations. Thanks to the E department, thanks to KICS and KAUST. And I'd like again to invite you to visit our research center in communication systems and sensing, and hope that this is just a start, and what comes would also be great. We'll have forums about sensing, localization, and radars, and the convergence of communication. So thank you, everybody, and we'll see you soon, inshallah.
Thank you very much.
Thank you, Dr. Ali, for amazing.
Yeah, thank you very much. Thank you very much.
Thank you.
Nice meeting you all also.
Okay.
Thank you very much.
Thank you.
Okay. Thank you very much. Assalamu alaikum.
Okay, so I will close this session. Thank you very much all, and sorry, Dr. Slim, for not being able to answer his query. Okay. Okay.